I did that 9. Yeah, they were my brother. Oh, that one would be the second one, second, third. I got That's yeah. Oh, it's all like these guys. They're almost like all over the all right, let's do this. Oh, really? Yeah. Ready? Yes. Image weighting in contrast in MRI. This is a significant lecture. A lot of material to cover. And it's building off chapter 1, right? So hopefully you're starting to really have that chapter 1 stuff sink in, because you need that to understand this. So we got to understand why is it weighting? What does that mean? Why does it say that? And first of all, what is contrast? So what was that?
Weighting is giving preference.
There we go. Well,
Giving it more weight.
it's giving preference to something. It's giving more preference towards T1 or T2 contrast, essentially. So yeah, we can never eliminate all of T2 or T1 information out of any image. So if we have a T1 weighted image, we're trying to maximize T1 contrast and minimize T2 contrast, or we're trying to weight it towards T1 information. We'll always have some T2 information there, but we're setting things in such a way that we're trying to minimize the T2 information and maximize the T1 information, thus weighting it towards that information that we were getting. There's different types of contrast information that are all going to be present on every image that you get. We just weight it towards one or another. So to understand that, we must first understand what is contrast. So you look at the definition of contrast, it's the state of being strikingly different from something else in a juxtaposition or close association. Being able to see the difference between objects is important in seeing anything, right? If we were all blue standing against this wall, you wouldn't see anybody, right? I could have a beautiful painting on here, painted in the same color blue, and you would not see it, right? Doesn't mean it's not there, you just can't see it. Right? In MRI, we want to see contrast because we want to see the differences between different tissues and different pathologies, right? That's how we see that there's something there. We have to have contrast. So you can see this is just an example of contrast. low contrast here. There's actually a difference in color between this dot in the center here and the box on the outside. It's just slightly, you can barely see it, right? The border, there's high contrast there. You can see the border of it, but if the border was gone, you probably wouldn't be able to really see this little more of an oval in the center here, right? Medium contrast, there's a subtle difference here, but you can see it a little bit better, right? And then high contrast is definitely a huge difference between these two different colors, right? That they're contrasting. You say to compare or contrast, you contrast things, you talk about how different they are, right? What are their differences? In imaging, it's the differences in color or shades of gray. 'Cause MRI is pretty much just different shades of gray. We have white on one end of the spectrum, black on the other, and all the shades of gray in between. All right, image weighting, right? Contrast in MRI is achieved by taking advantages of differences in T1 and T2 times of different tissues. Remember we talked about that before. Every tissue is going to have a different longitudinal recovery rate, different T2 or transverse decay rate. Also, they all have different amounts of protons within a given volume. Remember, to get the NMV, it's a bunch of little magnetic moments, also known as protons, right? Right. So if you have more protons or magnetic moments, you're going to have a higher NMV to start off with. Every tissue is going to have a different amount of proton density. We call that amount of protons in a given volume proton density.
Is voxel kind of similar to like pixels or?
Yes, we will, but we're not going to talk about that yet. But in MRI, it's volume imaging. We never see something that's 2D. We're always exciting a volume or a three-dimensional area. So voxel is volume pixel. It's two words together. Yeah. So like I was saying before, however, T1, T2, and proton density properties are present in every MRI image. So if you're looking at a T2 weighted image, there's some properties of T1 and proton density in there. If you're looking at a T1 weighted image, there are some T2 and proton density properties as well. And we're looking at proton density weighted image where we have T1 and T2 information there. We just want to weight it so that it looks more like one or the other, right? So that the contrast comes from T1 relaxation or T2 relaxation or from just the amount of proton densities, right? So we take steps so that image contrast is weighted towards T1 relaxation, T2 relaxation, or proton density. Following me? Here are examples of an axial of the brain, T1, proton density, and T2. You can see difference of contrast there, right? T1, dark CSF, right? CSF is basically water, right? So dark water, bright fat. You can see white gray matter contrast here. You look at the T2 weighted image, it's almost the opposite, right? That fat on the outside is dark, bright fluid. The white and gray matter contrast is different. And proton density, this one doesn't have a ton of contrast, right? Everything kind of looks very similar here. You don't see the ventricles as well as you do like in say T1, T2, or T1, right? So proton density kind of in the brain, it's not a great contrast, but we do still have contrast. You can see differences in grayscale there, right? Between the ventricles and the white and gray matter. It's just being derived from how many protons are within a given volume. We'll talk more about that in a second, but hopefully you can all see that these have different contrasts. Different tissues look different depending upon whether or not it was weighted towards T1 recovery, T2 relaxation, or just proton density. So to understand contrast, we have to talk about intrinsic contrast parameters. Intrinsic is inherent to the tissue. Write that down. What are your intrinsic, whatever, I can't think of a good example. But intrinsic just means it's part of the tissue's being, right? It's part of its being there. There's nothing we can do to change intrinsic contrast parameters. We can't change the T1 relaxation time of a tissue. We can't change the T2 relaxation time of a tissue. We can't change the amount of protons are within a given volume of tissue. Don't worry about these last two because we're not going to talk about them today, but flow and apparent diffusion coefficient, we'll talk about them more in physics too, but they do affect, we can't change how fast blood is flowing through veins, right? Or through arteries. We can't change that. That does get us contrast and other types of advanced imaging. We won't talk about that yet. We're worried about these top three today, so you can just ignore those for now. So, molecular tumbling rate. This is an intrinsic contrast parameter that affects T1 and T2 decay. So think about the molecular tumbling rate as the vibration on a molecular level. So you think about molecules, like this is not exactly what it is. You sort of have to understand the physics of chemistry to sort of really get the idea of what a molecular tumbling rate is. Kind of like spin, same thing. It's kind of something that's a little bit abstract, but you can kind of think about it as a vibration on a molecular level, right? Or an oscillation on a molecular level. So water has a particular molecular tumbling rate, and fat has a different one. They vibrate at different frequencies. If the molecular tumbling rate matches the Laramar frequency, or is pretty close to it, then we're going to have the more efficient transfer of energy. Kind of think about it as a reverse resonance. So if we have all the protons sitting there processing at a particular frequency, and then the molecule is vibrating at that same frequency, we're going to have an efficient transfer of energy between those protons and the molecular lattice. I know it's hard to imagine, but remember, T1 relaxation is also spin lattice relaxation, right? It's energy being released from the protons back to the molecular lattice. If that molecular lattice is vibrating at a very similar rate that the protons are processing, that energy is going to transmit from those protons to the molecular lattice quicker. And it'll speed up T1 relaxation, right? So when the nuclei and the molecular lattice is efficient, there is an efficient transfer of energy, just like there is in resonance, right? It's sort of a reverse resonance. Kind of think about it like that. When they don't match each other, it's going to take longer for T1 recovery and T2 decay. So if you're not fully understanding that, just understand there is a vibration on a molecular level. We call it the molecular tumbling rate. And if that molecular tumbling rate matches the Laramar frequency, then we're going to have more of an efficient transfer of energy and affect T1 and T2 decay. Okay. This one's easier to understand. If molecules are more closely packed together, right? If they are closer to each other, because molecules have space in between them, right? Think about like putting something in a box. You can cram a whole bunch of stuff into a box, or like say your trash at home, right? It looks full. Oh, it's not full yet. Pack more in there, right? Getting more stuff into the same volume, right? With molecules, you might have some stuff that are just closer packed together, right? If they're closer packed together, you're going to have more T2 decay happening. Because remember, spin-spin relaxation is exactly that. It's spins affecting each other, causing that decay of transverse magnetization, right? Those spins are going to affect each other easier if they're closer together, right? So if we have more closely packed together molecules, we're going to have more efficient T2 decay, meaning it's going to happen faster, right? So fat, think about fat and water. Which one do you think has the molecules more closely packed together? Fat, right? So fat is going to have quicker T2 decay because those spins are going to be reacting with each other faster. Proton density. Density is essentially how much stuff is there in a given volume. So say I have a cup of water and the same cup filled with fat, they're both filled to the same line. There is going to be more protons in fat than there is in water in that given volume. Same thing with the trash can analogy. If I have my trash can is full, and I push it down and pack more stuff into it, the volume didn't change, right? The trash can's the same size, but the density changed because I packed more stuff into it, right? So same thing with proton densities. How many protons are we packing into a particular area? Different tissues have different proton density, right? Fat is more proton dense than water. Meaning if I have 1 cubic centimeter of fat and 1 cubic centimeter of water, there's going to be a lot more protons in that cubic centimeter of fat. If I have the same amount of fat and the same amount of water, which one has the higher NMV, fat or water? What creates the NMV? Protons, right? If there's more protons, it's going to have a higher NMV. So fat, if you take a given volume of fat and a given volume of water, fat is going to have the higher NMV in that same volume. Just because it has more what? What do we call that? Proton density, right? Write that down too. Fat has the highest proton density of any tissue in the body. That is a very important part of the MRI signal that we get. Even though we're mostly water, a lot of protons in fat. Feeling okay about intrinsic contrast parameters? Okay, so what are the other ones? Opposite of intrinsic is extrinsic. These are parameters that are outside the tissue. And these are parameters that we can change. That's why I have these dials here. Dial it in. This looked cooler than an MRI scanner. These are the parameters that you as a technologist can change. TR, TE, flip angle. These are things that in the user interface, you can go in and change them. They are intrinsic contrast parameters. The reason we change these is to get different contrast. That's the whole point of it. TI, turbo factor, B value, they have an effect as well. We will not talk about any of those. So just cross them off the list and tell physics too. Okay. So once again, we are dealing with the top 3 here.
A question, so flip angle is controlled by how much RF energy is put in.
And the duration time.
And duration.
Yep. So remember, we can do a 90-degree flip angle. That's when we've talked about, we'll talk about other types of flip angles as well. The higher the flip angle, the more energy we have to transmit, or the more RF, or for a longer period of time. So it ultimately turns out to more RF, right? It's either a higher amplitude of energy or the same amplitude of energy for a longer period of time. Before we get into this, though, we need to start to understand the spin echo pulse sequence at a little bit greater of a, in more detail, I guess we should say. Greater understanding of the spin echo pulse sequence. We talked about it already, right? Remember, these echoes are things we are collecting. We have to collect several of them, right? And to collect them, we excite, and then we listen back, and then we do it all over again, right? Excite protons, 90-degree RF flip, and then we collect the data. What time do we collect the data in? The peak, but what do we call that from here all the way to here? That's the TE, right? We can control when we listen back, and then we wait, and then we do it all over again. When do we start doing it again? What do we call that time? That's the TR, right? These are just timing parameters. Notice though that we have 180-degree RF pulse here as well. There is a reason for that. Reason is because I didn't tell you until now, but transverse decay also happens because of inhomogeneities and susceptibilities, not just based on spin-spin interactions. So up until now, I told you that transverse decay happens because of spin-spin interactions, right? Also known as what? T2 decay, right? Actually, in reality, transverse decay happens much faster because of other reasons. Spin-spin interactions are happening, but other things are happening as well, causing a rapid decay. And if we try to listen back without refocusing, which is what this is, we will get information of transverse decay based on all of these other things and not just T2. So to see true T2 information, we have to refocus, and we'll get here in just a second. This is a spin echo sequence. I'm gonna show you this little video real quick. Actually, before I play it, think about it like this. 90-degree RF excitation pulse. We have transverse magnetization right here. It quickly dephases. Remember, that's the loss of the transverse magnetization. It quickly dephases because of inherent inhomogeneities, magnetic susceptibility. Go back to last week. What is inhomogeneity again? It's an uneven magnetic field, right? Measured in parts per million, but it's never perfect. We never have a perfect even magnetic field strength, right? To have phase coherence, thus transverse magnetization, we have to have all the protons in phase and continue to persist in phase, right? But what if the magnetic field strength isn't even? Are they going to persist at the same frequency? They're not, right? The Larimer equation says B0 times the gyromagnetic ratio. If B0 is all over the place, the precessional frequencies are going to be all over the place, right? So inhomogeneities are going to cause protons that are in phase to go quickly out of phase. Right? So we have transverse magnetization. Remember, it goes away because of loss of phase coherence, right? So anything that causes that loss of phase coherence is going to cause loss of transverse magnetization. And that is inhomogeneities. And remember, magnetic susceptibilities. What does susceptibility mean? Or magnetic susceptibility? Yes, it's tissue, anything in the magnet that changes the magnetic field strength, right? So susceptibilities are going to change the field strength as well. What happens to the precessional frequencies? They change, right? And everything goes out of phase. That loss of transverse magnetization or phase coherence that is not due to spin-spin interactions is something called T2 star. The loss of phase coherence or the dephasing of protons that were pushed into phase, going out of phase because of magnetic susceptibilities and inhomogeneities is something called T2 star. But we can eliminate that by taking a 180-degree refocusing pulse and flipping all of the protons 180 degrees through the transverse plane. So think about it like this. This is my transverse magnetization. It starts to go away because the protons are processing at different rates, going out of phase, right? Some of them are processing faster over here. Some of them are slower on this side. If we flip them 180 degrees, precessional frequencies didn't change. Now I have the fast ones behind and the slow ones in front. So they're gonna come back together, rephase or refocus. So that's what this is right here. Whoops. Right here, 180-degree refocusing pulse. 90 degrees in phase, boom. They start to dephase very quickly due to inhomogeneities and susceptibilities. There are true T2 interactions also happening, but it's happening much slower than the dephasing due to inhomogeneities and susceptibilities. At some point, we decide to boom, flip it over 180 degrees. Now the fast ones are behind and the front and the slow ones are in front, and they all come back together. Except for they don't come perfectly back together because true T2 interactions don't get rephased. We can't touch them. That happens anyway, which is good, so we can get T2 contrast. Well, here we go. Take a look at this real quick. Hopefully this video will help you kind of see it a little bit better. 90-degree right here. Boom.
Okay, starts to decay away, so they're out of phase. So if we were measured at this time, we see the signals diminishing.
Right, so you can see right here, this is the transverse magnetization, the golden arrow or yellow arrow, right? All these other arrows represent where the individual magnetic moments are pointing, right? They're a transverse component anyway. They start to dephase. The overall transverse component is dephasing, right? Why are they dephasing here? Due to inhomogeneities and susceptibilities causing them to persist at different rates. Some of them are faster over here, some of them are slower over here. Continue.
They get out of phase, it tends towards zero, and then we flip them around the other way. In the rotating frame reference, those fast ones catch the slow ones, and there we go. That's sort of bada bing, bada boom. They refocus. and we measure now, the signal comes back.
So you can
And if
see,
you let it go further, the signal goes away again.
I'm gonna play it one more time, but now you can start to see why it's an echo, right? It's coming back into phase, so that signal is growing again, right? They go perfectly back into phase, or almost perfectly, and then they dephase again. That's why it looks like that, as opposed to, that's why the signal looks like this, as opposed to just dephasing, right? Coming back into phase, signal gets greater until they are back into phase. That's the greatest, that's the peak of the echo at the TE, right? And then they go back out of phase again. Because remember, they're never processing at the same frequency, they're at different frequencies. They just go out of phase and then we push them back into phase, we refocus them. But they're only gonna be back into phase for a split second until they go back out of phase again. I'll show you one more time.
Question, so at this time, is the vector still, decaying?
Well, it decays, and then it comes back in, right?
So
It comes back into phase, and then it decays again.
oh,
But it never comes perfectly back into phase. As you can see on this video, you'll see when he measures the echo, the individual protons are not perfectly back into phase. So take a look at this. At the beginning, they are.
Okay,
Everything's
starts to
perfectly in
decay
phase.
away, so they're out of phase. So if we were measured at this time, we see the signals diminishing. Goes, they get out of phase, it tends towards zero, and then we flip them around the other way. In the rotating frame reference, as fast ones catch the slow ones, and there we go. That's sort of bada bing, bada
They're
boom,
not
they
perfect though,
refocus,
right?
and we measure now, the signal comes back. And if we let it go further,
So you let it go,
The
it
signal goes
diminishes
away
again,
again.
right? They don't come perfectly back into phase because we can't reverse true T2 decay. The spin-spin interactions are still gonna cause them to decay. We can reverse the inhomogeneities and the dephasing due to inhomogeneities and susceptibilities, right? We can eliminate the T2 star effects, but we can't eliminate true T2 interactions. You guys wanna watch it one more time? Okay. 90-degree excitation pulse, boom, push the longitudinal magnetization. into the
okay,
transverse
starts to
plane.
decay away, so they're out of phase. So
Immediately
if
starts
we were
to
measured
decay.
at this time, we see
Due
the
to
signals
inhomogeneities
diminishing.
and susceptibilities.
Goes, they get out of phase, it tends towards zero, and then we flip them around the other way. In the rotating frame reference, as fast ones catch the slow ones, and there we go. That's sort of bada bing, bada boom, they refocus, and we measure now, the signal comes back. And if we let it go further, the signal goes away again.
We could actually do another 180 at that point, and have them come back together again.
That's what I was gonna ask, can we just do it again?
Yeah, we could do it again, and we do. But that signal is gonna decay even more. It's not gonna come as back into phase because what is happening simultaneously? True T2. T2 is happening. T2 spin-spin interactions can't be reversed. The only thing that can be reversed is T2 star. This is dephasing. Due to what?
okay.
Right, inhomogeneities. And susceptibilities, two words that I don't spell very well. T2 is dephasing due to spin on spin action. Prime. This is not reversible. The spins interacting with each other cannot be reversed. This is happening on a quantum level. This is a good thing for us though, because the longer we wait before we refocus, the more true T2 interactions are going to happen, and the less in phase that transverse magnetization is going to be. Some tissues hold on to it for longer than others. That's where we get our contrast. Don't worry if you're not completely understanding that yet. We'll get there. Just want you to understand now, T2 star, that's dephasing the immediate loss of signal due to inhomogeneities and susceptibilities, right? And hopefully you're understanding it a little bit deeper. You're understanding that the loss of transverse magnetization is because the protons are going out of phase because they're processing at different frequencies, right? And if they're doing that, we can flip them 180 degrees, getting the fast ones to be behind the slow ones so that they catch up with each other. And this is at exactly twice the time as when we transmitted the 180. So here. The time from the 90 to the 180 is exactly the same time from the 180 to the peak of the echo. So this time equals this time, which that means half of your TE is the time between the 90 and the 180. And the reason for that is because the same amount of time we're allowing them to dephase is the amount of time it's going to take for them to rephase, right? So 90 degree, flipping the transverse magnet or the longitudinal magnetization of the transverse plane, they start to decay immediately. The protons, the individual protons, the transverse magnetization is going away, decays almost completely away very quickly. We flip it 180 degrees at one point through the transverse plane. They come back and catch up with each other at the TE time. We're eliminating dephasing due to T2 star effects, but we will still be left with some dephasing due to spin-spin interactions. We can't eliminate those. Yes.
Do we do the 180 flip in order to make it longer for the T2? We can look at it like longer. Is that why we do the 180 flip?
We do, well, we want to see, if we want to get true T2 information, we have to eliminate T2 star information.
Okay.
But yes, we also want a longer TE if we're looking for the differences in dephasing times, right? So if I want to look at the signal at 100 milliseconds, I wouldn't be able to if I just let everything dephase. I have to refocus it and get it to come back together. So yes, partially, yeah, that's, if we want a long TE, we want the protons to be in phase except for the true T2 interactions. Here we go. I know this is complex, but we'll get through it. Let's read through this. Why do we use the 180 degree refocusing pulse? I just explained it in my words. Now I'll read other words that I wrote down at a different time. In previous weeks, you learned that transverse decay, dephasing, is due to T2, spin-spin interactions, right? And that is true, but it's not the whole story. The protons lose phase coherence due to magnetic field inhomogeneities and susceptibilities, as well as spin-spin interactions. This stuff, the T2 star dephasing, happens much faster than T2 spin-spin interactions. So dephasing due to inhomogeneities and susceptibilities causes the transverse magnetization to go away very quickly. The 180 degree refocusing pulse eliminates the dephasing due to T2 star or the T2 star effects. So the 180 degree takes this away, takes it out. We don't have to worry about it anymore. Now when we measure our signal, the dephasing that we see, or the size of the transverse component of the NMB, is going to be reliant upon spin-spin interactions. True T2 spin-spin interactions. Of T2 star. Hopefully this will kind of help you understand it. No magnetic field is completely homogeneous. Cannot be. You try to get them there with shimming, passive and active, but it's never perfectly homogeneous. Also, we add material, body or whatever we're scanning to the magnet, it has susceptibility. It's going to change the field strength, right? So it's never going to be perfectly even. These mechanisms cause the protons to decay quickly. So you can see here, here's a perfect homogeneous field. Everything's in phase. It's going to stay there until that, and for an infinite amount of time, unless true T2 interactions are happening. But this is the real field. We have slower over here and faster, or lower field strength here, faster over here. You can see protons, when they're pushed into phase, the ones that are processing slower are going to slow down. The ones processing faster are going to speed up until eventually they lose phase coherence. We can graph the loss of signal over time, right? So if we did a 90-degree excitation pulse and turned on our receive coil, we would see a lot of signal right off the bat, right? Because we'd have 100% transverse magnetization. So let's say this is the 90-degree RF excitation pulse. We're gonna have, let's say we turn on our receive coil right away, we would see a lot of magnetization, right? Decaying very quickly. Right? We'd have a lot of current induced in our coil, and then it would go less and less and less until there was nothing, right? Because we are losing that transverse magnetization, right? We're losing that oscillating transverse magnetic field. If we graph the loss of that signal, that is called the T2 star curve, right? T2 star decay curve. You can literally measure that. We just turn on a receive coil after a 90-degree pulse. We just measure how that signal goes away. That is the T2 star curve. Notice it looks different than an echo. It didn't grow, right? It just shrinks. We start off with no signal until we cause resonance. We excite via resonance. Get a lot of signal that decays quickly. Once again, why is it decaying so fast? There we go. Inhomogeneity susceptibility is causing the protons to process at different frequencies. Rapid loss of transverse magnetization. We call that T2 star decay. T2 versus T2 star. T2 star effects cause the free induction decay. So you heard the FID, I think you read it in chapter 1. I didn't go over it a lot, but that is the free induction decay. T2 star causes the free induction decay, right? If there was no T2 star, this signal would stay a lot longer, right? But because we have inhomogeneities and susceptibilities, that rapid loss of signal due to T2 star effects is called the FID, free induction decay. I know it's a weird three words together. Just saying induction, right? Induction in the coil by the transverse magnetization is freely decaying. Goes away. We're not doing anything to keep it in phase. If we refocus the FID, like we saw in that video, with a 180-degree RF pulse, we will collect echoes that also have diminishing signal strength. So you can see here, loss of magnetization, but you can see it 180-degree pulse right in the middle there. We get the echo. Look at the peak of this echo versus the peak of the free induction decay. Is there more or less signal? There's less, right? Why is there less? $90, $180. Right. We get an echo, right? This peak is lower than this peak, right? Why do you think that is? We already talked about it, but I'm hoping you can recall. Yeah, because spin-spin interactions are happening. So when they come back together, they don't come back perfectly into phase, because at the same time as the dephasing due to inhomogeneities and susceptibilities, spin-spin interactions are happening. They can't be reversed. So you can see, if we wait a short period of time, we're going to have an echo that's still pretty large, right? If we wait even longer, the next echo is going to be what? Even smaller, right? Because more T2 interactions are happening. More true T2 decay is happening. If we draw a line between the peak of all these different echoes, that is now our true T2 decay curve. Following me, hopefully? Do this thought experiment. Say we lived in some crazy perfect world where there was perfect homogeneity and no susceptibilities. We excited. It would not decay at this rate because T2 star doesn't exist in this imaginary world, right? So what it would decay at would be the T2 rate. Right? Which would match exactly right here. So it would decay at a slower rate. But we get that same amount of signal here if we refocus, right? We just didn't need to refocus in this imaginary world because there were no inhomogeneities and susceptibilities, right? So in reality, because of T2 star effects, our signal decays very quickly, rapidly, right? We didn't want to listen back to the signal yet because we want to wait for whatever reason. We'll get there. 180-degree refocusing pulse, put it back into phase. It goes back into phase, but not completely. Depending on when we do it, it's going to be less and less signal. If we wait forever, eventually we're not going to get anything to come back into phase because a lot of true T2 interactions happen to completely cause dephasing. Here we go. T2 star effects cause the free induction decay. If we refocus the FID with successive 180-degree refocusing pulses, so several 180-degree refocusing pulses, we will collect echoes with diminishing signal strength. The loss in the signal strength between this, the next one, and the next one is due to what? True spin-spin interactions. 180-degree refocusing pulse can't eliminate true T2 effects. And that is great for MRI because we're able to now contrast, T2 contrast. Because not every tissue is going to decay at this rate. Remember, we have different T2 decay times. Some tissues, if we have a TE here, will be weak signal. Other ones will still have a lot of signal because their molecules are further apart and they weren't reacting with each other as fast, right? Here, 180-degree focusing video. I'll open this real quick. This is also in your Canvas. These videos exist there. So. Phasing, see the coil losing transverse magnetization, so that free induction decay happens. 180-degree focusing pulse. Now the faster ones are behind the slower ones. They eventually catch back up. I don't love this video because they actually go perfectly back into phase, which doesn't really happen. Grand Prix video. Imagine cars driving around a track. Some of them are going faster than others. They're going to go out of phase, right? Then imagine they did 180 degrees immediately and went back and started going the opposite direction. It's not a perfect metaphor or analogy because the protons don't reverse their direction. They just flip 180 degrees, but this could maybe can help some of you understand this. Cars pushed into phase at the beginning of the race, right? We're gonna have some of them that are faster than others. They're gonna immediately start going out of phase. Like the protons, some of them are processing at higher rates than others because they're in stronger areas of the magnetic field. Go out of phase. 180-degree flip. Cars are out of phase at that point. Turn the cars around 180 degrees. Slow one is still going to be going slow, but it's ahead of everybody now, right? Faster one is behind, but it's faster. They come back together. Same amount of time between the beginning of the race and when they went 180 degrees is the same amount of time it takes them to come back into phase. Right? Feel free to watch those videos. Gotta be some questions at this point. You got. I know it's hard to formulate the question, but it's fine. And just more graphics from your book showing it happen. Everyone understand the 180-degree refocusing pulse? Why do we do it? What does it do for us?
Eliminates T2.
Eliminates T2 star, right? Causes it rephases the protons or refocuses them so that they come back into phase. Do they come perfectly back into phase?
No.
No, because there's still some dephasing due to T2 star, or true T2 effects, right? Also, an important point is 1/2 of your TE, because remember our TE is excitation to the peak of the echo. 1/2 of our TE is when we transmit the 180. So you as a technologist, if you pick a TE of 50 milliseconds, when is the machine going to transmit the 180-degree focusing pulse? Yeah, 1/2 of 50, right? So at 25 milliseconds, boom, it flips them around. It's going to take another 25 for them to come back into phase, and that would be the peak of the echo. And once again, you as an operator can change that time to see more or less true T2 effects, right? If I take longer time or prescribe a longer TE, I'm going to see more I'm going to see more T2 interactions happen and get more T2 contrast. I prescribe a TE lower and transmit that 180 much quicker. Not many true T2 interactions are going to happen. It's going to minimize my T2 contrast. All right, yes.
So pre-induction, the only happens after the 90 degrees?
Yep. I mean, if you're looking at the echo dephases. It's not called the FID, right? But it's happening at the same T2 star rate. The rate it comes back into phase and dephases again on every echo is that T2 star decay rate. But yes, the FID is only the first thing that happens. It's this pre-induction decay right after the 90. We don't measure the FID. In MRI, we have to collect an echo. The physics behind image reconstruction, we want to see the echo come into phase and then back out of phase. We want symmetry there. That has to do with the way we're reconstructing essentially waveform data into an image. But we never sample the FID to create an image, ever. Timing parameters. We talked about this, but let's do it again. TE, so the 90 to the peak of the echo, right? TR, 90 excitation to the next excitation pulse, right? TR, repetition time, the time from one RF excitation pulse to the next. This is all review, but it's good to go over it again. It controls T1 weighting. Controls the amount of T1 weighting we see or T1 contrast we see on the image. TE, our echo time. Time from the RF excitation pulse to the middle of the echo. The echo always occurs at a time that is double the time between the 90 and the 180, right? So your 180 is 1/2 of your TE, or the time the 180 is transmitted, the 180-degree refocusing pulse is exactly 1/2 of your TE. This controls the amount of T2 contrast we see on the image. And hopefully by the end of this lecture, you will see how that works. TR and TE are prescribed in every type of image. So write this down. Some people think because TE controls T1 weighted or T2 weighted contrast, that in a T2 weighted contrast, I don't prescribe a TR. Or I'll say that a little bit different. Some people think that because TR controls T1 weighting, that I don't need to prescribe the TE, but you do, right? So think about, let me say it this way. We say that TE controls T2 weighting, right? But there is a TE prescribed in a T1 weighted sequence. We say that TR controls T1 weighting, right? But there is a TR that is prescribed in a T2 weighted sequence. Every type of contrast weighting has a TR and a TE. But they need to be used correctly so that we see the contrast we want. So think about it this way, TR and TE, TR controls T1, TE controls T2. If I have a TR and a TE in every sequence and I want T2 weighting, I need to set my TR so that it eliminates T1 information. Right? I don't want to set my TR to where it gives me T1 information. I want to eliminate T1 information with my TR. It controls T1 contrast, but I can set it to either show T1 contrast or eliminate it. So in a T2 weighted image, I'm going to set my TR to eliminate T1 information. And then I'm going to set my TE to show T2 information. We'll go, I know some of you are getting confused by that. It's fine. We'll get there. Just understand that TR and TE are prescribed in every contrast weighting. Proton density, T2 and T1. We're always going to prescribe a TR and TE. They just have to work together. And we know now our TR controls T1, TE controls T2 information, and we need to use them together so that we can see the contrast we want to be visualized on the actual image. So take a look at this. You're going to find different graphs out there that have different rates. The actual values don't matter. I don't need you to memorize these values. These are close. But these are tissues and their T1 and T2 times. Notice, all of these tissues that you would typically find in a volume of imaging in a body have different T1 times, right? Also notice that all of these tissues have different T2 times. And notice that their T1 and T2 times of the same tissue are also different, right? What do you notice about the difference between T1 and T2 times of the same tissue? So let's look at muscle. What do you notice about the T1 time versus the T2 time?
T2 is always shorter.
Yep. So what do you get? What kind of information do you get from that? What does that let you know? It lets me know that transverse decay happens much faster than longitudinal recovery, right? Or that dephasing happens much faster than the regrowth of longitudinal magnetization. Right? So my water is going to recover back to 100 to 63% of its original value at about 4 seconds after a 90-degree flip.
Water takes longer.
Its transverse magnetization is going to decay back to 37% in only 2 seconds, right? And every tissue has different times, right? So if I waited, if I had a volume of if I was imaging a volume that had water and fat in it, right? And I waited 1 second until we listened back to the signal, water isn't even going to get back to that 37%, right? It's going to be halfway there. It's still going to have a lot of transverse magnetization. Fat, on the other hand, it only took 70 milliseconds. It's not going to have any transverse magnetization if we wait 1 second from excitation until we listen back to the echo. So water will look bright and fat will look dark after 1 second from excitation. We'll go over this more. But the reason I want to show you T2 and T1 are different, right? T2 happens much quicker than T1 because you will see these reflected on your TR and TE and the times. T1 times are longer, much longer in most cases than T2 times, right? Meaning T2 decay happens much faster than longitudinal recovery, as it says right here. And what controls T1 information? TR, right? Since it takes longer, our TRs are going to be much longer. You're going to see them being much longer than our TEs. TE being the mechanism or the extrinsic contrast parameter that controls T2 decay, or the amount of T2 decay we see before we collect the data. Let's take a little break. Real quick though. T1 and T2 times of different tissues are different, right? The T1 time of every tissue is different from another tissue, except for, proteins and fat are close. Also, the T2 times of different tissues are different. And the T1 and T2 time of the same tissue are different, right? I want you to start trying to visualize what's going on here. Think about what the dynamic process that is happening. Try to visualize it. We'll get there. All right, let's take a 5-minute break.
Yeah.
Yeah, milliseconds, 1,000 milliseconds is 1 second. So that's how short these things happen, right? So 4,000, that 4,000 milliseconds of the T1 time of water is 4 seconds. 1, 2, 3, 4, right? That fat that decays in 70 milliseconds, that is less than 1/10 of a second. It gets back to that. So this is why this stuff is happening so fast. Why the machine's so loud, because all these things are happening at a very rapid rate. Radiate pulses.
How long are scans typically? Is it like 30 to like an hour? 30 minutes?
Nowadays, to like one pulse sequence, so like an axial T2 weighted image is probably around 3 minutes. It can be less or more, but I would say average is probably 2.5, 3 minutes. And then every single protocol has at least 5 different sequences contrast. So so I'll tell you, a typical knee scan is an axial proton density, 2 sagittals, 1 T1, 1 T2, and 2 coronals, 1 T1 and 1 T2. So 5 sequences total, about 3 minutes each. So 15 minutes of scan time. It can be faster or slower depending upon your equipment that you have.
How many patients do you usually see in a day?
At an imaging center?
Yeah, because that's a 10.
They probably do a lot of places now, because these are getting faster with AI. They're doing like a scanner. They're trying to do one every 15 minutes or per hour. That's crazy though. I don't think that'll ever catch on.
Yeah, like it's all.
One with this AI and not pushing the AI for quality, but more for speed. That's doable. I don't like it because they're gonna pack the schedule in and then somebody's gonna be claustrophobic and take longer and it's gonna throw everything off.
Yeah.
It's typically 30 minutes per scan. That is, I mean, we're gonna have to get, because businesses and hospitals are, every year they get less and less reimbursement from insurance. So to actually make a profit and have this work, they're gonna have to get faster. They have to put more people through quicker.
What does that say about the AI and like us? Like, are our jobs gonna become obsolete with AI, becoming more advanced?
No.
Wow. There goes my 40,000 down the drain.
It's gonna take time. And eventually this is what it's gonna look like. This is gonna be the first thing that probably won't happen for another 15 years from now. We're gonna have less techs controlling more scanners. You're always gonna have somebody on a scanner, but they're gonna be like a tech aide, somebody who's less qualified. Yeah. I'm gonna say it's about 15 years from now though, until it gets to that point. I mean, it could be faster,
Yeah.
but you're always gonna need a tech. It's just AI is gonna make one tech be in charge of more.
So it should be.
Gonna allow for one tech. So the better techs are gonna have better jobs.
You're just gonna have to learn how to manipulate AI after that.
Well, I mean, the AI, the things that the AI help with right now are basically just image quality improvement, right? So you can do, your scan times are gonna get quicker, and you're also, or you can take that and just make better quality images. The AI denoises and sharpens images, and it's FDA approved now, so it works, you know? And then also AI helps planning, and it helps, like, you know, you have to plan certain angles through the brain, you know, through the IACs. The AI can recognize it and plan it for you now. Can also help you, like, strategize your sequence, there's different strategies that you might need to take, and the AI can help with that too.
Oh, yeah.
Also, there's remote scanning that's happening now, to where you have somebody setting somebody up, sitting by the scanner, and then you have some tech in an office somewhere running 5 machines at once. Mark Boston, who might be one of your, when you're doing your labs, he usually does the labs, he does that, so that he sits in an office or like with a hill somewhere and like scans like off for five people at once. So you always have they have students and less experienced techs line, like, who are getting paid less, setting them up. Yeah. Students are still scanning other things. He only really needs to scan the advanced scans. Or things that are hard to teach or take a long time. Like cardiac or like certain dynamic studies.
Question.
Yeah.
Let's say, if we open a tax for McKesson. And, usually it says who's the radiologist who's reading, the name of the person who's reading. But if it says unknown, that means is it AI or not?
So you work at a place right now, maybe it hasn't been claimed yet. The AI is really not reading the scans yet. It's helping radiologists, so what it can do, what the AI can do at this point is it can go through, and it's not MRI yet. It can quantify and do measurements, but like for lungs, lung scans, it will give the radiologist out of hundreds, it'll say, look at these 10 right now.
So my
Right.
question is, have you ever seen these wordings? Where it says unknown in PACS or McKesson?
I mean, you're probably looking at a different PAC system there's so many different PAC systems, right? If it says unknown on the reading radiologist,
Yeah.
they just didn't claim it yet, probably. Their name isn't in there yet. If you gotta look at the report. If there's a report, it's gonna say a radiologist's name on there. But maybe PACS wasn't used correctly, maybe they forgot to put their name just in the system. I'm not 100% sure what you're looking at.
Brian, get a better understanding, but PRTB, you manipulate how many TDs within that same waveline, or
Just, there's one TD and one PR.
okay.
Yeah. Yeah. But even if it's at the time.
You wait up a certain amount of time.
Yeah.
Okay.
Yeah.
You did the repetition.
Yeah.
Yeah.
Did anyone come up with anything you want, or is there anything you want me to reiterate or try to explain a little bit differently or better?
It's not a question about if it's water is, it is 4,000 to the second. It will take longer, but it's not what we want, it's a better image.
No, this is a common question. So you're on, you know, good, you're thinking about this stuff, which is good. We don't want everything to have the most signal. If everything had a bunch of signal, we wouldn't have any contrast, right? We want some tissues to have a lot of signal and others to not. We want to have a range, we want to have a contrast, right? So that we can see the differences.
When I see 4,000 versus 2,000, looks like 2,000 is takes, I mean, 4,000 takes longer.
Well, you gotta think about what this is too. This is the T1 time of a tissue, right? So this is the time it takes for water to go from zero, right? And it's gonna recover, right? Recover, right? Over time, that's its longitudinal component regrowing, right? That is the time it takes for 63% to recover, right? From zero. Right? So we're waiting 4,000 milliseconds. Or at 4,000 milliseconds after a 90-degree excitation pulse, water recovered its longitudinal component to 63%. That's all that is saying. And then it's also saying that its transverse component went from 100% back to 37% in 200 milliseconds, right? And this is H2O we're looking at here. So that's what it's saying. It's just showing you the different times, right?
It takes longer, huh?
T1 recovery takes longer than T2 decay, but there are, remember, these are two independent, yeah, thank you, two completely independent mechanisms that are happening, two different things are happening. This is transverse decay, or the measurement, or how long it takes for transverse decay to happen. This is a time measurement for how long longitudinal recovery is taking to happen.
A millisecond is a thousandth of a second.
Yeah, that's a good question too. So, yes.
T1 was 4 seconds.
Yep.
Okay. That seems like a long time.
No, it actually. Yeah, I mean, water takes longer for everything. And these times, like I said, these times aren't exact. You're gonna find different values in different books. I think, I've heard before, it takes 16 full seconds for full longitudinal recovery of everything. It takes 16 seconds to get back to equilibrium. We're never really waiting that long for anything. But yeah, look at ice. For some reason, when you freeze water, T1 time gets a little bit longer, but look what happens to its T2 decay. Happens at 0.001 milliseconds. So you can't really scan ice, I guess. It's gonna decay faster than you'll be able to get the signal back.
Can you see water at all at 3,000 milliseconds? Because then wouldn't they be out of phase at T2? So would it even be possible to see it? They're out of phase.
Well, remember T2 is we're still gonna have 37% left at 2,000. So would there be anything left at 3,000? Not much, but maybe a little bit. That would be our TE time though, right? Yeah, we never prescribe TEs that are this long. Our we'll talk about that in this lecture too. You're gonna see our TEs are much shorter so that we could still get signal back. Anything else? Good questions. Talk about T1 relaxation and TR. So you have to, when we're talking about this, you have to have in your minds that if TR is a time, right? It's just, we're literally talking about a time. Like I'm gonna wait how long between excitation pulses. I can determine that. That's that amount of time, right? We can have short TRs or we can have long TRs, right? We'll talk about what a long TR means and what a short TR means, but we're generally gonna say a short TR is gonna mean there's gonna be a more rapid succession of RF excitation pulses, right? Short TR means I'm not gonna wait as long between times when I excite again. So I excite once, again. A longer TR would be like excitation, excitation, right? So when I say short TR, you gotta think more of a rapid fire of excitation pulses. Long TR, much slower fire of RF excitation pulses. So what happens with a short TR? If RF excitation pulses are applied at a rapid rate, we're not allowing for longitudinal recovery to happen, right? Because remember, it takes a certain amount of time for that longitudinal recovery to happen. So if we have a short TR, we're not allowing longitudinal recovery to occur. Especially for tissues with long T1 times. If it takes a long time to recover, right, and you excite again, you don't have much to flip into the transverse plane, right? On the other hand, if I have another tissue that just recovers really quickly, boom, you're gonna have a lot to flip into the transverse plane, even with the short TR. Remember, tissues recover at different rates. This is my longitudinal recovery. We start off here, right? Start off at equilibrium, we flip both of those in the transverse plane. Let's say we did that, we waited, decayed. We're gonna have longitudinal recovery, right? Let's not look at our transverse component. Let's look at just our longitudinal component. First excitation pulse, boom. Well, how much longitudinal magnetization do I have? Zero, right? We're gonna wait. Go this way. Some tissues are gonna recover back faster than others, right? If we wait a short period of time, tissues that take a long time to recover are not gonna have a lot to flip back into the transverse plane again. Remember earlier in this lecture, I was saying transverse magnetization is not only dependent upon phase coherence, but how much longitudinal magnetization we have to begin with, right? So at a short period of time, first excitation pulse, zero longitudinal magnetization. We wait, some tissues recover quickly, others take a long time, we flip again. Tissues that took a long time to recover or have a long T1 time don't have a lot of magnetization to flip back into the transverse plane. And thus produce what? Low signal, right? So with a short TR, tissues with a long T1 time will not produce a lot of signal because they don't recover longitudinally quick enough to flip anything back into the transverse plane. However, tissues with a short T1 time, tissues that recover back quickly, will have a lot of longitudinal magnetization to flip back into the transverse plane and produce what? High signal, right? With a short TR, we can get T1 contrast. This is called T1 contrast because we are getting contrast based on the differences of what? Also known as T1 recovery, right? So with a short TR, some tissues are going to relax back quickly longitudinally, are going to have a quick T1 relaxation time. Other tissues are going to have a long T1 time and not recover. And when we flip again in a short period of time, also known as a short TR, we're going to have the tissues that recovered quickly longitudinally producing a lot of signal, and the tissues that took a long time to recover longitudinally saturated with energy and not producing a lot of signal. Now you'll see the word saturated with energy, right? Remember, longitudinal recovery is a loss of energy. Remember, T1 recovery is energy back to the lattice, right? So that those protons are popping back up here, losing their energy, longitudinal recovery. If we saturate them with energy and they keep energy, that longitudinal component will not regrow. Therefore, there will not be anything to flip or not very much to flip back into the transverse plane, and it is not going to produce signal when we listen back to the echo. Or when we collect the echo. We're not listening. I always say that, but it's just an analogy, right? When we collect the echo. Using a short TR will give us T1 contrast, T1 weighting. That's what we need to do with our TR to get T1 weighting. Prescribe a short TR. We need to keep exciting these protons, these tissues, over and over again at a rapid rate to keep the tissues that take a long time to recover saturated with energy so that they don't produce signal. On the other hand, tissues that regrow quickly, even though we're going to excite at a rapid rate, they won't be saturated because they have very short T1 times that recover, and we have a lot to flip back into the transverse plane. I know some of you are having a hard time visualizing it. Understand this though. Remember, TR controls T1, right? A short TR is going to give us T1 weighting. But you also have to know what tissues are going to look dark and which ones are going to look bright.
That will be read on T1.
Yep, because fat has a quick T1 time, right? Or very short T1 time. Any tissue with a quick longitudinal recovery or a short T1 time is going to look bright on a T1 weighted image with that short TR. Tissues that look dark have what? A long T1 time, right? It takes them a long time to recover longitudinally. Right? They barely recover. We're gonna wait a short period of time. We haven't let them recover yet longitudinally. We flip that back into the transverse plane. There's not much there, right? And they look dark. So tissues that look dark on a T1 weighted image have a long T1 time, right? So go back here. Which ones are gonna look dark and which ones are gonna look bright with a short TR? Dark or bright? Dark, right? Because it's not gonna recover very quickly. We're gonna saturate it with energy and not have much to flip into the transverse plane. Gray matter. Gonna be kind of saturated with energy, right? Depending upon our TR, but it's gonna recover quicker than water, so it's gonna look a little bit brighter than water, right? Well, fat. Right, it's gonna recover super fast. Like we said before, fat looks bright on T1, CSF looks dark, right? And the reason for that is because we prescribe a short TR. Saturate these with energy. These can't get saturated because they let loose of their energy quickly. I don't love this. This is straight out of the book. It does show you your longitudinal component, but I like to look at them as separate, right? I don't like to look at this vector going down here. But you can see your longitudinal component, right? If we wait a short period of time, water is not regrowing very quickly or as fast as fat is, right? So when we flip again, you can see that longitudinal component of water goes into the transverse plane, and it's much smaller than that longitudinal fat that was flipped into the transverse plane. Therefore, bright fat, or a lot of signal from fat, little signal from water, signal being current induced in the coil, right? See, water, the blue arrow takes longer to recover longitudinally because it has a long T1 time. And that short amount of time, when another excitation pulse is applied, at a short TR, water becomes saturated and fat does not. This allows fat to produce high signal and look bright, and water to produce low signal and look dark. Thus, we enhance T1 weighting with what? Short TR, right? Don't talk about gadolinium yet. Gadolinium actually reduces the rate of T1 recovery in water, making it look bright at a short TR, but we'll talk about that next week. How do we get T1 weighting? Short TR. And the tissues that look bright are tissues with a short T1 time, right? That recover quickly longitudinally. Tissues that are dark are tissues that hold on to their energy for longer, don't recover as fast, have a longer T1 time. So how do we get rid of T1 information? Long TR, right? Even if tissues have a different recovery rate, right? So this one relaxed back quicker, but we're gonna wait. This one finally recovers back, we flip again. Is there any difference in signal intensity based on T1 relaxation times? We wait. These are both the same size, right? Short TR, boom, flip again. Contrast, right? Tissues that recovered quickly are going to be bright. Tissues that took a long time are going to be dark. We don't change the intrinsic contrast. They're still going to have the same amount of, or this is still going to take the same amount of time to recover longitudinally. We're just going to wait longer. So excite. Excite again. Contrast? No. No, not based off of T1 recovery. They all recovered fully longitudinally. There's no contrast at that point. So to eliminate T1 contrast, we do what? Long TR, allowing all tissues to fully recover longitudinally. With a long TR, T1 weighting is diminished, right? So if I want T2 weighting, I want to diminish T1 information, right? That's why your T2 weighted images have a long TR. We have a TR. Following me? You have to understand what a TR is, what T1 is, what T2 is to understand this. So hopefully we're there already so that we're starting to get this. All right, how do I get T1 contrast? Short TR. What tissues look dark? Why? Why does water look dark on a T1 weighted image? It has a longer T1 times. It takes longer to recover longitudinally and gets saturated with energy. So that when we flip it back into the transverse plane in a short period of time, there's not much there to flip. Right? There's not a lot of longitudinal magnetization to flip back into the transverse plane of water in a short TR because we didn't allow it to fully recover. If we want water to fully recover, what do we need to do? You have to wait a long period of time, right? If we wait a long period of time, everything will fully recover and we will lose T1 contrast, which we want to do for other types of contrast. Check it out, video.
Down into the longitudinal axis, into the transverse plane. We've given them identical T2s because we can, because it's graphics. So they decay away at the same rate in the transverse plane, but we've given them different T1s. So in this sample, we've given the yellow tissue a rapid T1, the short T1, and the green tissue a longer T1.
So between those two, yellow and green, which one's fat, which one's water? Right? Yellow's fat because it recovered quicker longitudinally, right? Now, if we flip them back into the transverse plane before this fully recovers, he doesn't have the graphic here, but I'll let him continue to speak.
So what would happen if instead of waiting for these things to remagnetize completely, if we put another excitation pulse into the system now? Well, this, and I don't have a graphic example, is the yellow vector would project down the same size it is here, and the green one would too. And when we then measured the signal, the yellow vector would give off approximately twice as much signal as the green vector. And we'd be able to discriminate between these two tissues based on their different T1 relaxation rates.
Thus contrast
Okay.
based on T1 relaxation.
So to get a T1,
I didn't cut it off. The video just cuts off. What do you think? You know how we get T1 contrast now?
down into the long.
T1 contrast. Short TR, right? Tissues that look bright are tissues with a quick longitudinal recovery or short T1 time. And then the opposite's true. Tissues that look dark have a long T1 time. They take a long time to longitudinally recover, right? And if I want to eliminate T1 information, if I want to eliminate T1 contrast, I need to allow for everything to fully recover. How do I do that? Long TR. And once again, these are parameters that you as a technologist can change. You go on your scanner, you can change that value. We don't know ranges yet, but you're going to need to know them by next class. So they're there at the end of this PowerPoint. We'll talk about the ranges. So TE. TE controls what? T2 contrast, right? So it controls the amount of dephasing we allow to happen before we listen back to the echo. If there is a long period of time, this is known as a long TE, between RF excitation and the refocusing pulse, thus the center of the echo that we get, We collect an echo with a large amount of transverse decay. Right, and because we use the 180-degree focusing pulse, the decay is due to what? If we use a 180-degree focusing pulse, so what is the decay that we measure based off of? True T2 interactions. So in a spin echo sequence, which is the one we were talking about, with a 180-degree refocusing pulse, if we wait a long period of time between excitation and echo collection, we are going to have a large amount of transverse T2 decay happening with tissues that have short T2 times. Because remember, the longitudinal component is just part of the story, right? We have been ignoring this part of it, the transverse decay, right? So once we flip, immediately we start having the protons go out of phase. Ignoring the 180-degree focusing pulse, let's just pretend that's not happening. Protons are decaying. Some of them decay at a faster rate than others, right? So if we wait a long period of time, so I know it's going to confuse it because the 180-degree didn't happen. In reality, it goes like this. Boom. We flip it, go back together. Some of them are going to come more back into phase than others because of true T2 interactions, right? But I'm just pretend the 180 is happening. I'm just not going to show it because it makes it overcomplicated. Excite, we wait. One of them is going to decay back faster than the other one, right? So we wait a long period of time. Tissues that have a short T2 time will not produce a lot of signal, right? If we start listening back right now. Tissues that hold on to their phase coherence, thus have a long T2 time, will produce a lot of signal, right? They have a lot of transverse magnetization and look bright. To me, this is easier to understand, right? But this is happening much faster too. Therefore, tissues with short T2 times, such as what? You go back to that chart. Fat, right? Fat has a very quick T2 time in relation to water. I think water said it was 2000. Fat was 70, right? So fat decays back much faster. If we take a long period of time before excitation and when we listen back, fat is going to decay and produce what? Very low signal, right? On the other hand, tissues with long T2 times, water, CSF, hold on to their phase coherence for longer and do what? Produce high signal, right? So with a long TE, we get contrast based off of T2 decay times, and this is known as T2 weighting. So how do I get T2 contrast? Long TE, right? We wait a long period of time between excitation and the center of the echo. Right? So we know to get T1 weighting, we need a short TR. To get T2 weighting, we need a long TE, right? If I want to eliminate T1 information, I have a long TR. So how do you think I eliminate T2 information? There we go, short TE. So here's the signals diminishing for a long TE, right? We start off at 100% from all of them because we flipped everything into the transverse plane. And then we wait. Fat decays quicker, goes out of phase much faster. Water holds on to its phase coherence, produces a lot more signal. If we wait a long period of time, we are going to get bright water and dark fat. The blue arrow holds on to its phase coherence longer than fat, the yellow arrow. In a relatively long amount of time, when we listen back to the echo, also known as a long TE, water still has phase coherence, while fat doesn't. Fat has completely dephased or almost completely dephased and produces barely any signal. This allows for water to be bright or produce a lot of signal and fat to be dark or produce a little bit of signal. So thus, with a long TE, T2 weighting or T2 contrast is enhanced. So look at the short TE. If I excite 180-degree flip and listen back right away? Do I have differences in contrast here? No, right? As long as I started off in full longitudinal recovery, do I get any contrast? Not really, not based on T2 reactions. So how do I minimize T2 contrast? By listening back to this or collecting the signal right away, which is known as a short TE, okay? Excite, listen back right away, no difference in signal intensity based on T2 decay times. That's how we eliminate T2 information. So you can see right here, shorter period of time, there's still a difference in contrast here, right? Because we didn't wait 0 time. We had to wait a certain amount of time. Fat's going to decay a little bit. But the differences in signal intensity are a lot less here than they are here, right? So we are minimizing T2 information. There's still some T2 information here, just not a lot. So minimizing T2 contrast is done by shortening your TE. Yes.
That's the long TE,
Mhm.
the second line, is that when you would do the 180 flip?
No, so just imagine the 180-degree flip happening at half of that time. It's happening back here, right?
Yeah.
It's just not showing it because in actuality, this signal decays really quick, comes back, right? So this is just, we're just simplifying the explanation by not showing the 180 degree. You just have to imagine it happened at 1/2 of this time. Okay. But the signal, it doesn't decay like this either. That it would decay like that if there were no inhomogeneities and susceptibilities. But just simplifying the idea. So eliminating T2 information or minimizing it is done with a short TE, right? Maximizing T2 information is done by long TE, right? What if we keep waiting though? You get no signal at all, right? So eventually T2 information is going to completely go away if we wait long enough, right? We have this, there's a window there, right? We want to wait for a certain amount of time, right? We wait, this is a good time to get contrast, right? Back here wasn't to get T2 contrast. We get a lot of signal, but no contrast, right? Based on T2 decay. Wait, we get good contrast right here. If we keep waiting, this goes away too, right? If we wait too long, the contrast goes away as well. All signal goes away. And we end up with nothing. But there is a window there. We want a relatively long TE to get better T2 information. Very short TE is minimizing that T2 contrast. What tissues look bright in a T2 weighted image? Water. Tissues that hold on to their transverse magnetization longer, right? Yeah, water. Tissues that look dark are tissues that lose their phase coherence quicker, have a quick T2 time, or have a short T2 time, and end up looking dark. So is it a true statement that tissues with a long T2 time look dark on a T2 weighted image? No, thank you. It's because it can be tricky, right? I can say long T2 time, that means it takes a long time to recover transversely or to decay transversely, meaning that it holds on to its phase coherence for a long period of time, right? And produces bright signal. You gotta try to keep these ideas in your head. Brass tacks though, long TE, it gives us more T2 contrast. Short TE diminishes it. And then just know the tissues that are going to look bright or dark if we prescribe a long TE. So here we go. One last video, and then
Excited, they get out of phase, signal diminishes. If we were to measure it, we flip them over. And if we look at what happens with short echo time, they're almost perfectly in.
this is just going to show one tissue, but it's showing with one tissue at a longer TE what's happening, right? So this was a short TE. with the 180-degree flip, they went back into phase, but not perfectly, right? He's gonna wait, he's gonna do a longer TE. Do you think that tissue is gonna be more in phase or less?
In phase, but not quite. And we'll explain why, or I'll explain why that happens in a minute. They get out of phase and the signal goes away. If, on the other hand, we wait a longer period of time after we tip it from its resting state, we wait. They get more and more out of phase. And then we refocus it with a pulse which is stronger. When they come back together, they don't come back together as well. So we get a smaller echo. And the reason they don't come back together again is even though this gets rid of the inhomogeneous effects which are spatially distributed due to the inhomogeneity in the magnet, it does not take care of the effect of how one proton affects the other. That's called spin-spin coupling. It's not a reversible effect.
So I know this video didn't show you T2 contrast, but it's just showing you if you wait longer in a TE, even in between, even though we do that 180-degree flip, protons are still, the tissues are still going to diminish their signal over time because true T2 interactions are happening. Let's take a lunch. How long do you want? A half hour? 45 minutes. That's fine with me. We will come back at 12:15. Try to be back at 12:10 if you can. And we'll put these two together because remember, TR, TE are all integrating. Karate chop? Feel the karate chop? It's happening incredibly fast. Yeah. Now it makes sense. Yeah. Not crazy.
Probably
There's like a.
But it's like. There's only some 299 per year. Oh, really? After a year? Oh, yeah. I was like, debating mine, and she's like. I was like, honestly, it's like a habit. But it's I mean, it's more like a doctor, I know them, so they're like, yeah, yeah, I was like, I don't know why I chose to prepare for him. Between like my roommate and the relatives, they started that's his word, chill. Well, kind of. They don't work from home now? I don't work. She does surgery, she doesn't, she's like very back to back. I'm early, you're like I was so glad when I saw people. Take a walk, 5-minute walk, come back.
Yeah.
Okay.
It's cool.
I'll mind my boss.
I
just drink snack. I'm so sad about my game. It looks like somebody's like got that on it. I literally had it for a week and then I got it. Yeah, but I think this was very much. Yeah, I guess.
Usually want to go to Vegas. No, not yet. No.
Yeah, we used to have it that way.
Yeah.
We were literally. Yeah.
When was your birthday? When was it not? June coming up? You're going to Vegas?
I know that really is, but. Deep doesn't even know, but. No, it was just asking Katie. I feel like Katie was pretty young. I mean, she is young. She's only young. I'm usually the baby. Well, I'm 24, so I'm okay. But my dog was the baby. Was the baby. Oh, now everybody knew. Is there somebody you know? No, I just switched it up. Oh, so now I don't. Oh, I call it Chloe the youngest. Not the baby, but. Yeah.
No, the question of.
They're for like 20 plus years. I'm like, the amount of
I'd be like, I don't know, I'm from high school, man. Now I know. Tissue will also X-rays versus. Yeah. Like now. 2D versus 3D. Oh, man. No, I should go in somehow. We're. Told you my backup plan, MRI doesn't work out, right? Yeah.
No, but it was so
Good night, man. Gold mine. Hell yeah.
even some thought that.
Oh, you can do that.
I'll make some thought that in the
We'll
mind.
hire you for $15 an hour.
How do you do? Good, yeah. 26. I'll take it.
That's good enough.
Yeah.
How do you do that? This is you.
75.
You just, and plus a 50% for the
Yeah,
study.
last time I got 70 and I did the whole hour and I got like 85.
Mhm.
So, I mean, whatever.
Plus like, community development.
Oh my God, yes.
Gosh, it's the overnight class.
That's more stressing than this, actually.
Seriously.
Yeah, he gave me -3 points
For
because
discussion.
my resume had 2 pages and it had my name on the top of the second page and that's it. I replied back, I'm like, really, dude, you have deducted 3 points for a mistake? Yeah, I'm like, that, I tried to take it off, but I couldn't. I'm like, yeah, so I'm like, no, I mean, all right, thanks, I guess. So then he changed it and replied back by saying, oh, you know, I just want you guys to be perfect and yada, yada.
But you have to understand that we have stuff to do too, you know, and
Yeah.
that's the least of our problem right now.
Yeah. But I mean, it's fine, whatever.
I don't, I don't really care about that class, I have a C and I'm okay with it.
Yeah.
I don't even pay attention to it, if you write work, I violate.
Yeah,
I'll just take your blood.
yeah, I already got my recommendation letter
Check like.
and I'm gonna finish my thing tonight.
Like,
I can.
like, he makes it, do that social media thing, I get it.
Ask for all.
Like, why would you freaking like
You have-
try not page, like, do
Papers?
and
Yeah.
doors?
Yeah,
It's like, that's, I just go to therapy.
Just post up with it on it.
yeah, no, I don't know. What's the lunchroom? I'm trying to figure that out. Yeah, I want my soda. Yeah, right?
Right when you walk out that way, it should be on your left.
All right, so I did a whole fucking circle in it.
Okay, cool. No, I got a little worried with this one. This one was the practice MRI.
Oh, yeah.
Signature versus completed form, I think that was the practice. Like, here's the immunization form. You get a lot more than just this. I feel like this paper is outdated, because. Not the one that's. Yeah, me too. Like a big package, it's like a big. Yeah. It's stable. This before. I'm not down. There's not. Oh, it's not right there. There's a one. Oh, okay, so it's just the. Yeah. Yeah. So they do it physical. Consider that one. Do the MMR and all that, but then they also check if you have your measles vaccine, your mumps vaccine, your hepatitis B, hepatitis A, varicella, and rubella. To get all of these done as well. It's not just like something there. So you might be going in for a lot, and then you also gotta get your COVID booster, and you gotta get your flu shot as well. A little bit more than what that paper says. I think that's the one. Yeah, this is the first one. And then your doctor will make sure you bring this to them too. So you have to make sure he or she explains here to the state. Right.
But you have to get your COVID shot or like booster.
Yeah, you have to get the booster and the flu shot. It doesn't say here, but you do have to get the flu shot. I just talked with Simone. She said it's required.
So when you get it, are they gonna say, no, they're gonna write it down?
Yeah, they write it all down there. At the flu shot, you have to just get a separate paper. And then they have to check take your blood. And you also have to get like everything else that's required. So that's not on there. There might be like measles vaccine, or there might be, just a lot of other ones. But you just gotta get them all.
Oh, we actually, how is that?
Not really said, but it said right here, if you look right here, vaccines. See, like all these are measles, mumps, hepatitis B, hepatitis A, varicella, and rubella. So you have to have all these up to date as well. On top of this. They should pull your blood, like you just asked for that. They'll pull your blood and check for everything.
Like, can you check them? Like an annual checkup? Like-
Yeah, kind of thing. I didn't have all those other ones before. Like, I only had the ones from a while ago, so I had to get them all. Again, yeah. I have to go back for my chicken pox in like 2 weeks, once I get my Hep B and the flu shot. So, giving person.
Well, I feel like we probably got it back then,
Yeah.
but how would you have that? That's what we could do.
They check it with blood. That's why they pull your blood and they check if you have the correct antibodies. Like, I've had the chicken pox shot, but I was below what I could get to be. So I have to do it again, so I can get it.
So you just go to your doctor and give them this paper and have them to see what you need?
I told them, they were like, what do you need? I was like, oh, I'm gonna be starting clinical soon. So I need this for my MMR and just a lot of different shots in my physical. They said, okay, perfect. We'll get somebody to do all of that.
Thank you.
Appreciate it, yeah. I was just talking about this.
Then you have to get your hepatitis B as soon as possible, because you have to have your second shot before the end of February, and they take a month in between. So you gotta get your first one before January, and it's,
Which is like, well, first of all, yeah.
hepatitis B shot.
Yeah.
You have to get the Hep B as soon as possible.
Yeah, next week.
And you have to make sure you're free, like after 2 to 3 days, because when you go there, they're gonna give you a TB skin test, like they'll put a little bubble in your arm. And then in 2 to 3 days, you have to go back and you have to check if the bubble like didn't infect your arm or cause any redness. And once they do that, they'll clear you. You have to go back, so you have to make sure you're free.
Does it do anything in the body, like you get sick or?
TB skin test? No, it's just like this fluid, and they want to see if you're allergic to
Oh.
it. So they do it yearly at hospitals. So they just put like a needle underneath your skin, just put a little under your hand like this.
Oh, I used to feel like that.
It goes away after the day.
Yeah, I remember getting that.
Yeah, when I was a little kid, yeah.
The way that she did it, you submit 2 PDFs at the same time, so just the letter recommendation and then the next PDF with the references on it.
Yeah, because I'm like, how am I gonna add it in my?
Yeah, just do it in a separate. When did she do your?
So I emailed her, I think it was Monday, and then she didn't reply, so I'm like, man, I don't know someone else, you know? And then she just like emailed me back like, like 2 days ago. And she said, oh, he's gonna recommend.
Oh.
Information. They all like posted.
I know, I asked you, I should have done that, because I asked him to come to these, they're like, yeah, I'm gonna come Saturday, yesterday, she's like, I don't know if I'm gonna get done. But you're having to, it's great.
That's like teachers, like, teachers,
Yeah.
is there stuff? Work wise, they don't want to,
Yeah.
is there time?
Yeah, so I probably should have done that. But, oh, well, I won't have it this time, but he said that if you don't get our recommendation, we just have to see. Without, yeah.
Like, sorry. Like, sending me a English.
Yeah.
I think you get it, you
I mean, it's not their assignment, it's mine. I don't think it can be. I think it's just not like doing friends, and, you know. Mine, I want the good news off the word. But we didn't. Once, actually, the lines and.
More than
Yeah.
a lot of email. Yeah. Like, you know, yeah. No, I think it's. Pretty much everything.
Good. The avocado toast? Yeah, clear. It wasn't that good thing. Did you ask them why they came back? I didn't ask, but others said that. I guess I couldn't. Chick bought it, the one chick bought. Her mom. Oh, really? Her mom, works right now or something. Oh, yeah, she was something. But it's like, she's like struggling and like. One line or anything, just her letters. Right. Which I'm like, it's fine. She didn't make it as good, because like, I remember they used to do fun. And like, I think she just put like way too much. And, um, you go to your buckets? Huh? You go see your buckets? Yeah. I don't work tonight. I didn't work last night. I'm off Sunday night too, so. I'm like, yeah, it's good. Take advantage, I'm up here. Yeah.
I read this summer. It's like two in depth. Yeah. That's what I'm saying, so.
Pigments. Useless? Useless. Oh, okay. It's another docking reason. No. I'm good with it. Nice. Yeah. I'm good, John, with you. Second, this magnitude.
It's so traumatizing. I don't wanna do it. For this thing? Good. Good.
Yes.
Yeah. I should use the stuff for it. Those monsters fighting. There's all the money. Yeah, I mean, it's fun. It's good. You know, I know, right? We have a long sequence. I can't find it back. They just. That's.
I don't like that. I can't.
And now.
And you can see all that. That shit.
Yeah, I'm gonna do that. It's really not. And then you gotta like help me with just the fucking. This is beyond. I don't have. It's cool, but I mean, it's. Yeah, I'm down. You go to like. Right here, crash that over. They have it. That word and things. Doesn't matter. Yeah, you gotta help me with like. But I like it. Put on the ground, right? Yeah, like it's cool, but it's. Like when it's. At the same time, when I was making last one, I used to kid like build, like wrote on the wall and. So we can mouse right next to like an mouse is the one that do that. My lifetime, man. No, Macarena. Okay, like. Oye, legal, que esa persona. Exactly. Bro, like, there's no way that I'm not gonna study at least 2 hours. It's on a Thursday. I'm already exhausted. Yeah, I just.
I'm also just like.
The link.
Oh, wait, I already have. I have one. You already have one? Okay. Maybe it's so fun. Yeah, I have like. Yeah, I know. I have. I'm also just.
Oh, yeah, dude. I told my kids. Yeah, I told my kids, Sunday, I'm watching some. I'm like,
Especially that Chiefs game.
oh, yeah, dude. I'm going for
Let's
the
see it, let's see it drop down and finally beats Mahomes.
Yeah, I hope so.
Now that it's at his house.
I hope so.
I didn't have something that the field defense is weird. Two of their corners and one of the linebackers.
Yeah, but.
Field mopped.
Yeah, I told the twins, take care of each other, leave me alone.
So here's what I think. I want the Bills to win,
Yeah.
but I still think Mahomes is sneaking away.
You think so?
But I want Josh Allen.
But you have to really utilize his legs and really utilize kind of Messi and all his weapons, because if he doesn't.
Yeah, so last game that they played that the one beat up by 3 for the regular season, not playoffs.
Oh, yeah, this season.
It's Kansas City Chiefs didn't have a running back as they ever checked them. Now they do. So that's a game changer. He's a game changer.
Yeah. That's the late game, right?
3:30.
Oh, yeah, bro. Guess a winning thing.
Yeah, you can't miss it. You can't miss it.
And,
All right. Welcome back.
I didn't do that, sorry.
Any new questions after lunch? Anybody want to take that leap? No. Be difficult admitting that you don't understand, but it is fine. Took me a long time. You're thinking, it's not hard at all. Gotta formulate the question though.
Yeah,
That's the hard part.
That is the hard part.
I didn't, go through this once and I understand. So. Got us, that's been time. So, we went over T1, T2. We went over the TE, the TR, how they're related to each one. Hopefully all of you can kind of get it now, at least if I ask you a question, how do I get T1 weighting? You can say short TR, right? TR controls that T1 weighting. And then that short TR, hopefully you can tell me why you get the T1 weighting as well. With short TR. Short TR, what is that? That's rapid fire RF excitation pulses, right? What happens when we excite again? What happens to the longitudinal component of magnetization? There we go. It doesn't fully recover, right? So tissues with long T1 times that take a long time to recover are going to get saturated, not produce a lot of signal. On the other hand, other tissues that do recover quickly, that let loose of their energy quickly, like fat, right? Fat has a molecular tumbling rate that closely matches the Laramar frequency. So it allows for that energy to transfer into the lattice quickly. Lets it go. It's also it's closer packed together. Lets that energy go quicker. TE. How do I get T2 weighted images? Or how do I enhance T2 weighting? Long TE, right? We'll talk about the ranges in a little bit here, but yeah, that long TE is going to allow for tissues with short T2 times to decay. Are they going to produce signal or not? In the long TE, tissues with short T2 times are going to look what? Bright or dark? Dark, right? Because they decay away quick. Short T2 time, that signal's going to decay away, and we're not going to listen until after they decay. Other tissues that don't decay as fast, hold on to their phase coherence, thus transverse magnetization longer, are going to look bright in that relatively long TE because they hold on to that transverse magnetization for longer. So here we go. How do they work together? For T1 weighting, we want to maximize T1 contrast, right? How do we do that again? Short TR. Do we want to see any T2 contrast? We don't want T2 contrast in a T1 weighted image, otherwise it would be some sort of blend, right? So how do we get rid of that? Short TE, right? So we excite quickly and we listen back right away before any dephasings happen, or very little, right? T2 weighting. We want to maximize T2 information and minimize T1 information. How do we minimize T1 information? Long TR, right? We allow for what? What are we allowing for with the long TR? What kind of recovery? Right? Longitudinal recovery. We're allowing for full longitudinal recovery. What does that do? Minimizes T1 contrast. It's not there anymore. If everything fully recovers before we excite it again, there's no T1 information, no contrast based on T1 relaxation times. Maximizing T2 information, we have a long TE. We wait after excitation for a long period of time for some tissues to decay and others to hold on to their transverse magnetization. That decay is based on T2 interactions, right? That's why it's T2 contrast. So for T2 weighting, minimize T1 contrast, long TR, maximize T2 contrast, long TE. And then we can do proton density weighting. What should we do with the T1 contrast if we're trying to get proton density weighting? Do we want to minimize it? Yes, we do. How do we do that? Long TR. Do we want to minimize T2 information? We do. Short TE, right? Minimizing both of those types of contrast is going to give us contrast based on the amount of protons that are in the tissue, right? So now it's just going to be the NMV at equilibrium that's going to tell the difference, right? Because look, this is our NMV of fat, and this is our NMV of water at equilibrium. Remember, fat is the highest proton density, right? There's a difference, right? So we want to wait for full longitudinal recovery, which we do have at equilibrium. We can wait for that again with a long TR, right? And then when we flip, we want to listen back right away before any T2 decays happen, right? The long TR to allow for full recovery, and then short TE to listen back right away. We still have contrast because fat had a larger NMV to begin with, right? The contrast is just based off of what at this point? Yeah, the proton density, the amount of protons that were there to begin with. And since fat has some more protons than water does, it's going to be a little bit brighter than water. Contrast is very minimal, but this type of proton density weighting has the most signal. Everything's bright, right? Some are a little bit brighter than others based on the proton density, but there's a lot of signal here. We're not waiting for any dephasing to occur, right, or very minimal. And then we're waiting for full longitudinal recovery so we can flip everything back into the transverse plane again. So proton density, a lot of signal, contrast is it's not that great. Do what you need to do to memorize these ranges for now. TR. A short TR for T1 weighted spin echo sequences. Remember, we are talking about spin echo pulse sequence. The spin echo pulse sequence has a 90-degree followed by 180 followed by an echo. These are spin echo type pulse sequences. We're going to talk about a gradient echo sequence in a little bit, but spin echo T weighted parameters, short TR about 350 milliseconds to 800. Short TE, minimum or 0. You can never do 0 because remember we have to do a 180-degree flip, right? And that takes time, so it'll never be 0. But we can get it as low as possible, up to about 25 milliseconds. That's an acceptable short TE for T1 weighting. 90-degree flip angle and 180-degree refocusing pulse. That's how we know that it is a spin echo, right? Flipping our excitation pulse is 90 degrees. And our refocusing pulse is 180 degrees. Spin echo uses RF refocusing. We'll talk about gradient echo in a minute here. It's different. Some of you are saying, why is there a range here? We want short TR. Why don't we go back to 150 milliseconds? Can anybody guess why we might not want to do that?
FID.
Different tissues.
Some good guesses. But why don't we want to go back? Why do you think we don't want to go any lower than 350?
We want to give enough time.
You want to have for some longitudinal recovery, right? Right, if we flip, then we flip right away, neither fat nor water have recovered. You're not going to get any signal, right? We have to wait a little bit of time for that fat to recover, right? So that we can flip again and have some signal from fat and other tissues that have quick T1 times. But if we go too short, they're not going to recover at all. We're just going to end up with no signal, right? And no contrast. There's no signal, there's no contrast. So that's why you want that range. You don't want to go too short, but if you go too long, then everything starts to relax back and you start to lose that T1 contrast, right? Write these down because I am going to give you TRs, TEs, and I'm going to say, hey, what kind of weighting is this? There's going to be some questions on your next quiz. T2 weighted spin echo parameters. Long TR, 2,500 milliseconds and higher. Can I go to 5,000 milliseconds?
No? Yes.
Yeah, it's over 2,500, right? Nothing's going to happen if I keep waiting. If I have full longitudinal recovery, if I keep waiting, it's not going to change my contrast at all, right? Before we flip again. Right? Long TE, this is where we get the range now, about 80 milliseconds to 120. If we go less than 80, we haven't had enough dephasing to get really good T2 contrast, right? Fat's going to dephase a bit, but water isn't, and water, but just not enough, right? Just not an acceptable range to get the best T2 contrast. Why wouldn't we want to go over 120? Yeah, everything starts to decay. We start to lose too much signal and less contrast, right? So you want to have that range there. It's gonna say at the end of the PowerPoint, but these ranges are general and they can vary depending on what you're trying to do, right? But the reason we're memorizing these ranges so that we can do these exercises and figure out what we're talking about here, right? So don't take these ranges as like the Bible for MRI when you go out into the field. They're pretty decent, but it depends on what you're trying to do. There might be reasons why you want to go outside these ranges, and also different field strengths slightly affect these ranges too. So not a lot, but a little bit. But for our class, these are the ranges that are the truth. And then once again, it's a spin echo sequence, so 90-degree RF excitation and 180-degree refocusing pulse. Based on what we know now, can anyone guess what the TR and TE of a proton density weighted spin echo looks like? We want to eliminate T1 information, right? And how do we do that? So what do you think? Over 2,500, right? And then we want to minimize T2 information. How do we do that? Short TE, so what do you think that would be? Yep. There we go. Proton density weighted. Minimize T1, with the long TR, minimize T2 with the short TE. Now our image contrast is based purely on proton density. What weighting do we have right there? T1. T1. Now what do we got? Proton density, right? Now what do we got? T2, right? Gotta know those ranges. It's not that hard though. Just gotta memorize what ranges we're at. What's that? TR, short TE, we're within the range though, right? That doesn't exist. That's improper parameters right there, right? That's a short TR and a long T. Yeah. I'm glad no one said anything for a long time, so. Yes, this is trying to get T2, but this is trying to get T1 weighting. It's a combination of both. This would actually be very signal poor, because this is what we'd have. Short TR, right? So we'll talk about the first one. So dot would start to recover, right? Water wouldn't. We would flip again after a short period of time. We wouldn't listen back though right away, right? So this would just start to decay. There's not much water to decay. So even though it holds on to its transverse magnetization, there's not a lot there to begin with, right? Then we listen, no signal, right? So those are parameters. I won't trick you like that yet, but towards the end of the semester, I'm gonna give you improper parameters on the next quiz, but you gotta keep practicing this. That might show up, not that exact one, but.
Look like an artifact.
It'll just look signal, but it won't look like much. Look really dark. You won't see a lot. All right, here's my favorite video with the sweet guitar playing. This actually starts.
Because these protons in our bodies have different local environments, some associated with the free-flowing water molecules, while others are fixed in position associated with the structural or energy-storing molecules of protein and fat, they have characteristic differences in their T1 and T2 relaxations. We can accentuate and measure these differences by changing how quickly we put in the radio frequency energy, or the repetition time, designated TR, and how quickly we choose to listen to the signal coming back from the transverse magnetization, or echo time, designated TE, of the precessing protons. This process is referred to as the pulse sequence, and we will use a sample of fat and water to demonstrate these differences.
One has more proton density based on that picture right there. Yeah, right, like there's a lot more hydrogen in a smaller area than there is in water.
As before, to simplify and maximize comprehension, we're going to stop the precession of the protons. On the left is a group of spins or protons associated with fat, and on the right, water.
Be
When
more
we-
accurate, there should have been larger NMB here than there is here, right? There's more proton density on this side, but they didn't think that through.
In our resonant radio frequency pulse, all the protons absorb that energy, flip into the high energy state, and spin together to produce our 90-degree pulse or transverse magnetization. If we wait a sufficient amount of time, the protons will move apart in a T2 or spin-spin relaxation, and the transverse magnetization will decay. The protons associated with the free fatty acid, being relatively fixed in position, decay rapidly as the spins push away from one another. They also give up their absorbed energy more rapidly as they fall back to baseline in a T1 or spin lattice relaxation, depositing heat energy into the surrounding tissues and regrowing the longitudinal magnetization. On the other hand, the protons in the freely flowing water can hold on to their energy and continue to spin together in phase, thus maintaining the transverse magnetization. At this point, when we turn on our receiving coil and measure the signal coming back from the protons, the relatively large transverse magnetization in water will give a strong signal, while the smaller or absent transverse magnetization in fat will give a weak signal. By convention, the strong water signal will be assigned a grayscale color of white, and the weak signal of fat will be dark gray or black.
Also keep in mind when watching these videos is for simplicity's sake, they're getting rid of the 180 degree. It's happening, it's just not being demonstrated, because it just adds more complexity. Just know that anywhere, whatever your TE is in a spin echo sequence, there was a 180 degree refocusing pulse at one half of that.
Hence, to accentuate the different T2 relaxations of the protons in our bodies, we would wait a long period between radial pulses.
And once again, why do we use the 180 degree refocusing pulse? Bring back phase coherence and to eliminate T2 star information, right? Eliminating dephasing due to the T2 star effects.
Referred to as a long repetition time, TR, and wait a long time to listen for the return signal or echo, referred to as a long echo time, TE, and these differences can be measured and recorded. Using these same tissues in their baseline state, to accentuate the differences in T1 relaxations, we again put in our 90-degree resonant radio frequency pulse, which flips the protons into the high energy state and pushes them in phase to produce our transverse magnetization. T2 relaxation occurs as the protons move apart faster in fat than in water, and then the protons fall back into the low energy state, dissipating the absorbed energy as heat into the surrounding tissues and regrowing the longitudinal magnetization. Again, because the protons in water are fluid and move freely, they tend to hold on to that energy longer, and the protons stay in the higher energy state with little regrowth of the longitudinal magnetization. whereas the tightly packed fat protons more rapidly give up that energy and return to the low energy state, thus rapidly regrowing the longitudinal magnetization. If we then quickly put in another resonant 90-degree radio frequency pulse, the fully recovered fat protons will produce a large transverse magnetization and a strong measured signal that we can record if we listen to the return signal or echo shortly after the second radio frequency pulse. However, the water protons are still in a high energy state with little regrowth of the longitudinal magnetization. Therefore, the new radio frequency pulse flips more of the low energy protons into the high energy state and can only produce a small transverse magnetization as well as a net longitudinal magnetization oriented 180 degrees or directly up.
Don't even think about that. Just know it's not producing transverse magnetization because it only had a little bit of longitudinal regrowth, right? I want to think about it having some like anti-parallel magnetization, because this doesn't matter. We can't measure that anyway.
With the known magnetic field. This configuration in the water protons will give a low amplitude or low energy wave when we listen for the echo or return signal. In other words, the protons in the water are saturated with energy and can no longer produce a strong transverse magnetization. Therefore, to accentuate the differences in the T1 relaxations between the protons in fat and water, we want to rapidly put in our resonant radio frequency pulses or a short repetition time, TR, and quickly listen for the return signal or short echo time, TE. Now, this is a difficult concept and you may have to listen to it a few times to get it to sink in, but to summarize, the T1 relaxation effects are accentuated by rapidly exposing the protons to radio frequency energy and keeping the spins in the high energy state and thus reducing the effective longitudinal magnetization. Tissues that recover quickly will have a large signal, while those slow to recover will have a low signal. T2 effects, on the other hand, are accentuated by a prolonged echo time to allow the spins to move away from each other and accentuate the differences in T2 relaxation between regional tissues or chemicals. So a T2 weighted image is obtained with a pulse sequence of a long TR and a long TE, decreasing the T1 effect with the long TR and enhancing the T2 effect with the long TE. A T1 weighted image, on the other hand, is obtained with a pulse sequence of a short TR and a short TE, enhancing the T1 relaxation and minimizing the T2 effects. In between these two is the proton density pulse sequence, which is obtained with a long TR and a short TE, effectively minimizing the T1 and T2 effects, and basically giving us an idea of the absolute number or density of protons in the region. The first to propose the use of NMR
That's it. That easy.
to diagnose
Is it making sense at least? Following along? Right. This is gonna go outside this really quick, but this is kind of where, this is just a good point to sort of talk about data collection and something called multi-slice acquisition. Not gonna have too much on the quiz about this. It's gonna be mostly contrast and stuff we learned before, but this is, there's a reason this is in here now. You'll understand later. So image data collection. Remember I was saying before, we have to collect several echoes. We have to do this pulse sequence many times just to generate one image, right? And in MRI, when we run a pulse sequence, we have several images. So many echoes must be collected to create one image. We call the images slices in imaging. How many slices are there? How many slices we prescribe? Because we are literally slicing through the body, and they literally do have thickness like a slice of bread or something like that. We're not just opening the body and looking at it. We're taking a slice out. Has anyone ever been to the Bodies Museum before? Yeah, there's like If you haven't been, it's awesome. They plasticize all these like corpses and you can see like the inside of all these bodies. They have this one body where they cut up into axial pieces, but axially, and they like spread it out over like maybe the width of this entire room. But you can see a slice there because when they're cutting it, they're actually cutting slices out of it and it has a thickness. That's literally what we're doing with MRI, except for we're not seeing the depth of it. It's all projected onto two planes, but that's how we get the data. We have to excite protons. It has to be 3 dimensions of protons, right? It can't be infinitely thin. You have to be able to excite like a thickness of tissue. So that's why they call them slices. Typical amounts of echoes that we collect, 128, 224, 256, 320, 512. Some older systems limit it to around these numbers or variations of this. They're always going to end with an even number though, because we'll find that out later. But newer systems, you can pick whatever even number you want, kind of. But essentially this has to do with the resolution of the image. So it is something we prescribe as well. This is just saying we don't need to know all that yet. We're just saying to create one image, we have to collect many echoes, right? These are typical amounts, but they can be whatever. The amount of echoes collected is determined by the phase encoding matrix. So this would be our phase encoding number. Don't worry about any of that, but it is definitely correlated with image resolution. We'll talk about that more in future lectures.
Brian, just to clarify, the thicker the slice, the more proton density it will have, then better signal.
No, well, yes, the more protons. So, but don't confuse that with proton density contrast. But yeah, there will be more protons in a thicker slice and better signal. You're 100% accurate. It doesn't change the contrast though. The only thing that's going to change the contrast are the TR, TE, and flip angle. We'll find out. Typical MRI scan contains several slices. So looking like the sagittal through the shoulder right here, let's say there's 14 slices. This means we have to collect 14 slices, or to create 14 slices, we have to collect that many echoes that were required by the phase matrix, right? So if it was 256 to make one slice, we have to collect 256 times 14 echoes to finish up the entire scan, right? So we have to go through each TR that many times to collect an echo, to collect that many echoes to collect all the data we need to have 14 images at the end of this sequence. Don't worry about these numbers. I'm just throwing general numbers out there. All echoes are stored in some place called K-space. This is where the raw data goes. It's called K-space, K being the symbol for wave. Wave space is what it translates to. We are collecting waveforms, right, with frequencies. We'll talk more about K-space in upcoming lectures, but each slice has its own K-space that needs to be filled with a certain amount of echoes. If each slice needs 224 echoes, then there are 14 slices, then that equals 3,136 echoes that need to be collected to complete an entire sequence. Only one echo per slice per TR is collected in MRI. All right. So every time we this is the echo I collect at my TE. My TR is way out here. Remember, the TRs are much longer than the TEs, right? So we have to wait. We collect one echo. If I'm collecting 224 for one slice, it's going to take me a long time, right, to collect all of this data. Fortunately, in MRI, there's something called multi-slice acquisition, meaning that we don't collect one data for one slice at a time. We collect one echo per slice per TR. So you see all this dead time here? What we're going to do is excite the next slice. When that's done, we're going to go to the next slide because we have more time, right? And then the next slice. And then the next slice. Right? Because we have time. I've gotten here, I got to go back to slice one. So I ran out of room. whatever TR this is, it allows me to collect data for 1, 2, 3, 4, 5, 6, 7 slices before we have to go back. Right? So we're basically collecting one echo for 7 slices and whatever TR this is, right? I just randomly drew some lines up there that represent time. So I don't know exactly what the numbers are. We could calculate it though. If you calculate what your TR is and what your TE is, you can actually know when your next slice is and how long that's gonna take and figure out how many slices you get per TR. Following me? So in this case, with whatever TR that is, the machine would only allow me to prescribe 7 slices. If I needed 14, what would I have to do? Make the longer TR or do it all again. Go back and repeat it. So I'd have to do another acquisition or I'd have to make my TR longer. Following me? This is something that happens in your system. So here we go. Better picture. Can't see this color right here, but this is showing you. Here's my 90, 180 echo. This is the TR. You can see I can start my next slice here and my next slice here. In that case, we only had time for 3 slices. But one echo, multi-slice acquisition, 1 echo is acquired per every slice in a single TR period. Each slice receives RF excitation and an echo is received each TR period. TR and TE then determine how many slices are allowed. In this case, how many were allowed? 7, right? So if I wanted more slices, I could raise my TR. Also, if I lowered my TE, I could fit my next slice in quicker, right? So lowering your TE, raising your TR, all of those things are going to affect it. How many slices are allowed per TR. But we know that we can't go too long with our TR if we want a T1 weighted image, right? So those things we have to balance. So just think about a multi-slice acquisition is the thing you're dealing with. An MRI, a lot of techs, you'll add more slices and then all of a sudden the scan gets longer. And then we'll find out in a couple of weeks from now, scan time is TR times phase matrix, which is how many echoes we collect per slice per TR, times something called next. But then a tech will be like, oh, I added more slices, but my scan time went up. It's like, well, because your TR went up. That's why. It had nothing to do with your scan time equation still works. It's just that you added another slice down here. And the system said, can't do it. I'm going to automatically increase my TR to compensate for that, right? And then here's some actual numbers on it if you want to see. TR 400 milliseconds, TE of 20. What kind of image contrast are we getting? T1. That's T1, right? T1 contrast right there. Additional 5 milliseconds to receive the echo, because remember, the center of the echo is going to be at 20 milliseconds. We have to listen to data for a certain amount of time. We have to listen to each one of the echoes, listen to it. We have to collect a certain amount of data. So we are collecting data for more than just an infinitely short period of time. We're collecting it for a certain amount of time during the echo. So it's just saying an additional 5 milliseconds after the center of the echo to collect all the data that we need. We'll get into that more later though. About 16 slices can be acquired before the second RF excitation pulse for 1 slice if no other imaging options are used. So if we did the math there, which they didn't show us exactly, but we could figure it out. Just take 400 and divide it by 25, essentially. What do you get? 16, I'm pretty sure. Yep, so 400, right? So at 20, I can collect an echo at every 25 milliseconds, right? So if I can do that 16 times in a 400 millisecond TR. So what happens if I add that next slice? It's going to increase the TR, right? Because we have to go back to the beginning. We're doing all this, but we need to go back and excite this slice again. We can't excite multiple slices at the same time. It has to be one at a time. What kind of image weighting do we have here? T2, right? An additional 5 milliseconds. So we can see we have 30 slices available to us here. Right? Much longer TR. Even though the TE is longer, if you divide 2500 by 85, you'll get 30, right?
Question, are you exciting it uniformly or is it varied over time?
What do you mean?
Like every excitation pulse, is it always uniform at the same time when you started, or is it varied, or can it be variable?
Well, what do you mean by the how varied in what way? The timing?
Yeah.
No, the timing's always the same.
Oh, okay.
Otherwise, your contrast would change, right?
Okay.
Yeah, the timing's always gonna be the same. Your TR and your TE are always gonna be the same to get the desired contrast. that you
And
want.
that's like entered in, right? So that way it's.
Yep.
Fits, okay.
Yeah, so you literally enter your TR and TE as a parameter into your scanner. And it determines how long between here and here, and how long between here and here when we collect that echo back. So that's multi-slice acquisition. Like I said, I just want you to start picturing it. I'm not gonna ask you any questions about that on this quiz. But it kind of makes sense, right? If I have to collect one echo per slice per TR, I'm gonna run out of room with shorter TRs. If I have longer TRs, I'm gonna be able to prescribe more slices and collect data from more slices per TR. All right, now it's gonna get fun. Try to shake it off real fast. And come in with a fresh brain on this. It's not as complex as it's going to seem. That was the spin echo family of sequences. In MRI, there are two families. There are spin echo and gradient echo. And there are tons of different variations of these gradient echo and spin echo sequences. We're showing you the very basic kinds right now. What differs them is refocusing. Here is our basic diagram for a gradient echo sequence pulse. A couple of main differences. Most of the time, the excitation pulse is less than 90. And the other thing is that we are not refocusing with RF. So notice there's no 190-degree refocusing pulse. There is no other RF until our next excitation pulse. Can you see the difference between gradient echo and spin echo? But there has to be an echo, meaning we have to have a growth of transverse magnetization and a decay. Remember, all of our echoes look like this, right? They come back into phase and then they dephase again. We still need that in gradient echo sequences. So what do? We use the gradients to create an echo as opposed to RF. Think about what happens when we turn a gradient on again. There is a change in field strength across the distance, right? The FID is dephasing due to inhomogeneities and susceptibilities, right? If I turn a gradient on, it is another layer of inhomogeneity essentially, right? Now I don't have an even bore. I have a change of field strength. Even though it's predictable, it's changed, right? It's different here than it is here, than it is here, and vice versa, right? We have another difference of field strength, which is essentially an inhomogeneity. So what happens when we turn on the gradients and we have that inhomogeneity? Protons at the high side of the gradient start to precess faster, right? And protons on the other side start to precess slower, because remember, based on the Larimer equation, the stronger the field strength, the faster the precession. The weaker the field strength, the weaker the precession, right? So protons start to dephase again, right? Say this is the gradient we turn on. Stronger field strength over here, weaker over here. Here's my protons in phase precessing. These ones start to speed up and these slow down, right? Turn off the gradient, they're all precessing again, but now they're out of phase. Now let's say we turn on that gradient equal and opposite, which we know we can by reversing the polarity of the flow, right? We have the current flow in opposite directions now. So instead of the gradient being like this, it is now like this. Now our protons that were going faster slow down, and the ones that were going slower speed up. right? So you have a rephasing from the gradients. So that's what is happening. This is the normal T2 star decay. This is the FID, right? So now zoom in. This is our spin echo, right? Now we're zooming into the FID to look at this. Right? We're zooming in here. It's all happening in a much shorter period of time. The FID is intentionally dephased faster than it's already dephasing using a gradient application because it causes another layer of inhomogeneity, right? That layer of inhomogeneity can be reversed though by flipping the polarity of the gradient. Same amplitude, but opposite polarity. So you get a dephasing, flip the polarity, you get a rephasing, right? And that all has to do with the fact that we're changing the field strength. The protons are moving faster over here, slower here, and then vice versa, right? You get a dephase and then a rephase. All of this other T2 star stuff is still happening though, right? So you can see it dephases much faster when we turn on a gradient. If we didn't turn on that gradient, this would be the decay rate. But we turn on a gradient, boom, it causes it to dephase immediately. So there's no signal. Reapply that gradient in the opposite direction, we get it go back into phase within this T2 star curve and then dephase again. This looks like an echo, right? So this is our gradient echo that we get. The FID is intentionally dephased by a gradient, then is immediately rephased by an equal and opposite gradient. This effectively creates an echo within the FID. Where we normally just had the free induction decay that we didn't measure. Now we can turn a gradient on and then opposite, and we get a little echo that we can record and put in decay space. Why the hell would we do this? Speed, exactly. Much faster. There are other reasons as well, and we'll get into that. But yes, it was developed for speed. MRI, especially back in the day, when it first started, was insanely long. 45 minutes for one axial T2 through the head. That's all you get. Now, 3 minutes, 2 minutes, 3 minutes for an axial T2 through the head, right? But back then, they were trying to figure out ways to get data faster. Gradient echo was a great way to do that. Gradients can be applied much faster than 180-degree RF pulse. Shorter TRs and TEs were achieved. This is the whole point in doing it. Inherently faster scan times. Of course, there are sacrifices. Anytime you're gaining something, you're giving something too, right? What did we use the 180-degree for? 180-degree RF pulse. We rephased it, but what did it do for us?
T2 star down.
Right? We got rid of those T2 star dephasing effects. Did we get rid of them now? No. So the contrast that we get has T2 star effects inherently built into it. We're not eliminating them by using RF refocusing. Gradient refocusing does not eliminate T2 star. Because of that, we know that T2 star is dephasing due to what? Inhomogeneities, right? These sequences are much more sensitive to field inhomogeneities and susceptibilities. Also, there's much less signal. As you can see, if we look back here, these echoes have much less amplitude than a spin echo does, right? So this is our inherent trade-off right here. Write this down. Our two inherent trade-offs to having faster scans is that we have sensitivities to inhomogeneities and susceptibilities, meaning we're going to have artifacts in our images from inhomogeneities and susceptibilities. And we're just going to have inherently less transverse magnetization, which means inherently less signal, right? The third trade-off is that we can't achieve true T2 contrast anymore. Thus, when it's a gradient echo sequence, we're gonna call it T2 star weighting if we're going for T2. Because it's never gonna be T2 because we can't eliminate T2 star effects. Here are gradient echo pictures versus spin echo. What kind of weighting do we have in this spin echo right here? T2, right? Bright fluid here. Same exact slice. This is a T2 star weighted image. Looks similar, right? But it's the contrast is not exactly the same. It is T2 star weighted. Also, what else do you notice? What are we looking at there? We have a slice right through the IACs, right? Internal auditory canal. Do you even see it over here? Right? This is because this is a sinus area. This is air meeting tissue. Anywhere you have air tissue interfacing, you have a high susceptibility, meaning there is a great change of field strength where air and tissue meet. That is an inhomogeneity or susceptibility that we are not getting rid of. We're not eliminating with T2 star, right? So we've completely dephased this area, this signal, because we haven't eliminated T2 star effects. And there are a lot of them in this area. So sensitive to inhomogeneities. There's an inhomogeneity here. All my data is gone. Faster scan time. T2 star contrast, not T2. Image quality affected by inhomogeneities and susceptibilities, right? Inhomogeneities can't be compensated for, therefore it has a larger effect on the image contrast. True T2 weighting cannot be achieved. So if it is T2 star, it is a gradient echo sequence, but we can still achieve true T1 and PD. We just cannot achieve true T2 weighting anymore. So you're never going to see a gradient echo sequence that's called a T2 weighted image anymore. It's T2 star if we're looking for that. What are the advantages of gradient echo sequences? What makes a gradient echo sequence different from a spin echo pulse sequence? Using the gradients for what? For creating an echo, right? We use the gradient to dephase and then rephase the FID to create an echo within the FID. Spin echo sequence, we're refocusing the FID, right? All together with 180 degree refocusing RF pulse, right? What are the downsides of using gradient echo? Less SNR. And we can only get T2 star weighted images. And sensitive to inhomogeneities and susceptibilities, right? So how do we generate contrast now? Gradient echo sequences always have a short TR. Remember I was just telling you the TR was part of our scan time equation? The whole point in doing gradient echo sequences is to make the scan time shorter, so it has a short TR always. Always a short TR. If I always have a short TR, how am I going to eliminate T1 contrast? Because we just learned that a short TR gives us T1 information, right? Remember? T1 contrast comes from the fact that we've allowed some tissues to fully recover and others not to when we flip again, right? And that's done with a short TR. If I always have a short TR, am I always going to have T1 weighting? We know not, because we know we can get T2 star, right? We know we can get proton density weighting, so we have to do something else to eliminate T1 information. That is done with our flip angle. Follow me, keep following me here. Hang on, you're gonna get this. Since the TR is always short, to avoid saturation, thus minimizing T1 contrast, we have to have a lower flip angle. And to get T1 information, we have to have a higher flip angle. So watch this. If it's always a short TR, and I want to have T1 contrast, I just prescribe it like I normally would. I just prescribe a 90-degree RFX or a flip angle, right? So if I'm looking for T1 information, I'm gonna have fat recover quick, water recover slowly, we flip again, what do we got? What kind of contrast do we have here? Bright fat, dark water, T1, right? And then just listen back to the echo right away. Don't get any dephasing, that's T1 contrast, right? So if I keep a high flip angle with a short TR, right? So high flip angle 90 degrees, a little bit of recovery, we flip again, we have T1 contrast, right? If I want to get rid of T1 contrast, but keep the short TR, I just don't flip it as far. I lower my flip angle down to say 15 degrees, right? So I still have a lot of longitudinal magnetization left. So instead of going from here to 0, we go from here to here. Fat relaxes back quickly, water relaxes back too, and we flip again. So with a small flip angle, we're allowing for full longitudinal recovery even in a short period of time. So here we go. T1 contrast. We have a high flip angle still. Because the TR is short, that high flip angle is going to allow for saturation. Because fat will still recover back in that short period of time, but water won't. So it'll be just like a regular spin echo T1 weighted image, right? We have that large flip angle, which we do in a spin echo, it's 90 degrees, right? If we keep it at 90 or somewhere near 90, we're still going to saturate water and it will look dark. We also want to listen back right away so that not much dephasing happens, because we still don't want to see dephasing in a T1 weighted image, because that's T2 star information. So if we want T1 contrast in a gradient echo, TR doesn't matter anymore. It's always short. So just keep in mind, TR is always going to be short. I need to keep my flip angle high, somewhere from 75 to 90. The reason I say less than 90 sometimes is because our TRs go even shorter than 350. They can go down to like 100, right? But if I don't want to saturate everything, I got to lower my flip angle a little bit too. So just keep in mind here, this is like a regular spin echo sequence. Short TR with a high flip angle, 75 to 90, and a very short TE. Once again, what is the short TE doing for us? Yeah, in this, it's eliminating dephasing, right? And since we're not eliminating T2 star in a gradient echo sequence, we're eliminating the T2 star information that we're seeing here with that short TE. That high flip angle is going to allow for us, oops. It's going to allow for us to saturate tissues that didn't recover back quickly. Tissues that recover back quickly, fat, will show up bright still. I'm basically just saying the same thing I said before in a different way. We're eliminating the TR as a factor though now. TR is always going to be short. So to do a T1 weighted gradient echo sequence, we keep everything the same. High flip angle, 90 degrees or a little bit less. We have a short TR and a short TE, right? Same thing as before. For T2 star weighting, we need to eliminate T1 information. How do we do that? We need to allow for full longitudinal recovery. Since the TR is always short, remember, it's not long anymore. We can't have it long. It's a gradient echo sequence. The whole point is to have that short TR. So to compensate for that, to still get full regrowth, we just don't flip it as far. Instead of flipping it all the way down to here, we flip it maybe just to here. And it'll fully recover. Flip it again here, fully recovers in that short TR period. So to get T2 star weighting, we have to eliminate T1 information. We just do not flip the NMV as far. We lower our flip angle now. Lower the flip angle to allow for longitudinal recovery. Think about it as a head start to longitudinal recovery. You're putting somebody ahead of the race. Remember before, it took a long time to get back to longitudinal recovery. Right now, we just don't push them as far. We put them towards the finish line quicker by not flipping it all the way down. So it's going to recover in a shorter period of time since it doesn't have as far to go. Since we're not flipping the NMV as far, it's not going to take as long to recover. So even tissues with even tissues that take a long time to longitudinally recover will still recover because they didn't have that far to go. Like putting a slow runner at the end of the finish line and saying, okay, I'm not going to give you much time to get there, but it doesn't matter because they're going to get there anyway. They're right there. But then what we also want to do is prescribe a little bit longer of a TE. So now for T2 star weighting, since the TR is always short, we want to just flip the NMV from about 5 to 30 degrees. There's still a lot of longitudinal magnetization left, right? So it's not going to take that long to fully recover. But to get T2 star information, we have to wait for a little bit longer of a TE to allow for some dephasing to happen. So we do the same thing, a longer TE to get T2 star information and a low flip angle to allow for longitudinal recovery. What does this small flip angle do for us?
For more longitudinal recovery quicker.
Yeah, it allows for us to have full longitudinal recovery, even for tissues that take a long time to get there, just because we're giving them a head start. And what does that do ultimately? What does having full longitudinal recovery do for our contrast?
No T1.
There we go. Gets rid of our T1 information. And we want to do that if it's T2 star weighted, right? Now that we've eliminated T1 information with the low flip angle, how do we get T2 star information? Long TE, right? To allow for some dephasing to happen. Just keep in mind though, it's a relatively long TE because remember all of this stuff is happening back in the FID. So it's going to be shorter than it normally would have been in a spin echo sequence. This one doesn't really show much of a contrast difference, but you can see it. There's a flip angle of TR and TE are exactly the same here. They're both 720 respectively, right? TR 700, TE 20 with a 90-degree flip angle and then a 30-degree flip angle. You can see the contrast difference though, right? You see fluid better here. This is T2 star weighted. This is more T2 star. You can see the fluid up here. Here you don't really see it. It all kind of blends together. Check this out. This is changing our flip angle, but keeping TR and TE constant. We don't know exactly what the TR and TE are here, but we're just changing the flip angle. I'm going to say the TR is 500 and the TE is 20. 10-degree flip angle. Water fully recovers, right? It is not being saturated because it doesn't have that far to go back. Fat does the same thing. Flipping it to 30. What's happening to the contrast here? Look at the ventricles. Is it getting brighter or darker? Right? Fluid is getting darker. Now if we flip to 30 as opposed to 10, we still have a 500 TR, that water is not gonna come back as far. So when we flip again, it's gonna start getting saturated. Now we flip to 50. What's happening to water now? Much darker, right? It's becoming more what weighted, would we say that? This is probably T2 star, bright fluid, dark fluid now, right? So we're going from T2 star to what? More T1 weighting by doing what? Increasing our flip angle, right? TR is always short. By increasing our flip angle though, we're getting more T1 contrast. And you can see the TE affects it as well. TE from 10 to 50 here, more T2 star weighting, right? This is proton density. We don't know what the flip angle was. TR and flip angle remain constant as we increase our TE though. We have more transverse decay happening. And you can start to see more, this looks more T2 weighted, right? We have more contrast between fluid and gray and white matter than we do over here, by allowing for more dephasing to happen. Here are parameters. Once again, TR is short. So somewhere, let's say, if you guys need numbers, say from 5 to 500. It's always short. Our TE, as low as you can get it. Our flip angle is going to be high, 70 to 90. This is the main factor controlling our T1 information, is our flip angle on this gradient echo sequence, right? So let me show you this. TR, TE, flip angle, refocusing angle. Say my TR is 300 TR, long or short?
Sure.
Short, right? TE, 3, long or short? Flip angle, 75, long, high flip angle or low flip angle? High flip angle. I am going to saturate tissues with a long T1 recovery time, right? We know we don't have a refocusing angle, so what type of sequence is this? Gradient or pulse or spin echo? It is a gradient echo sequence, right? With a high flip angle and a very low TE. What kind of weighting do I get? T1, right? This is a T1 weighted gradient echo. TR doesn't matter anymore. It's always short. You don't even need to look at that anymore. Just look at your flip angle. If I have a high flip angle from 70 to 90, I know I'm going to be saturating tissues with long T1 times. I'm going to have a T1 weighted sequence right there. What if I do this? For T2 contrast, once again, TR short. TE, this is a relatively long TE now in a gradient echo world. 20 to 40 milliseconds is a long time when you think about the length of the FID, right? So once again, I have a long TE. What does a long TE do for me? Allows for dephasing. What kind of contrast do we get? T2 star, right? This is going to give us our T2 star information. We also have to eliminate T1 information, right? How do we do that? Small flip angle, allowing for full longitudinal recovery, right? So now, right here, TR, doesn't even matter, we know it's short. What kind of, well, it does matter. What kind of sequence do we have? What kind of pulse sequence? Without the refocusing pulse? Gradient. The gradient. Long or short TE? Long. long in the gradient world, right? 25 milliseconds. High or low flip angle. We're gonna have full longitudinal recovery, eliminate T1 information, right? T2 star information, eliminate T1 information. What kind of weighting do we have? T2 star. Not true, T2. We didn't get rid of T2 star. T2 star, it's a gradient echo sequence. Still a gradient echo sequence, right? We already know that because there's no refocusing angle. Long or short TE? Short. We're eliminating what? Yeah, so T2 star. High or low flip angle? Low. What have we eliminated? What do we get? What's the last one? I heard it. TD. Proton density. Right? Eliminated T2 star. Eliminated T1. See what else we got here. Once again, my disclaimer, general contrast parameters. These are just for us to play this game so that we can start to understand this stuff. I know it's a lot right off the bat, but that's what you get for taking classes once a week. Let's play some more. When you're playing this game, first of all, tell me what type of sequence is it? You have two different choices. Don't tell me the weighting, the types. There's two families. What family is this in? Spin echo. How do we know that? We use RF refocusing, 180-degree refocusing. What does this do for us?
Eliminates T2.
Eliminates T2 star. So I know the contrast can't be T2 star, right? It can't be T2 star because we've eliminated that. So I have three choices now. What are my three choices of contrast here? T1, T2, and proton density, right? Long or short TR? What has that done? Long, is this long? What has it done for us? Yep. What is this, long or short? Long, what has that done for us? It's enhanced T2, right? That's your answer right there. It's still spin echo, right? That's the first thing you have to do. We know it can't be T2 star weighted. TR, short or long?
Short.
Short, what has that done for us?
Enhanced T1.
Enhanced T1. Has this gotten rid of T2?
Yes.
It's short, right? It is destroyed T2 information. Fat. It's a T1 weighted spin echo. Long or short? What's that done for us? Killed our T1. What is this, long or short? What has it done for us?
Kill T2.
It's destroying T2. It's getting rid of T2 contrast, right? So what do I have? Yeah. What?
Grading echo.
Yep. Gradient echo. TR is, this is telling us that it's a gradient echo, right? No refocusing angle, and it's less than 90. So it's majority of the time, it's gonna be less than 90. Right, so now we're looking between this. We don't worry about that. What is this doing? Is this short or long for the TE in the gradient echo world? Short. What is that doing for us? What does the TE control? Right? What has it done to T2 star? Bam. We don't have T2 star now, right? So we know that it has to be either T1 or proton density weighted. What has this flip angle done for us? Is it high or low? It is high, right? With the short TR, which we're always gonna have, what does this high flip angle do for us? Yep. Not allowing for full longitudinal recovery in tissues with long T1 times, thus giving us T1 information. So what do we have? T1 gradient echo. Let's play it this way. I want T2 star weighting. What do I need to do with my TE if I want T2 star weighting? 25 will work, right? Because it's got to be between what? 20 to 40. That's going to allow for dephasing to happen to give me, because tissues are going to dephase based on T2 star at different rates as well. Right? What do I need to do now? I've got myself some T2 star information here. I need to eliminate T1 information. How do I do that with my flip angle?
Low flip angle.
Low flip angle to allow for full longitudinal recovery. Give me one.
15, 30,
15 or 30, I'll split the difference. I'll go 20. But you're right. Anywhere between about 5 and 30 would work. It kind of plays off of your TR. The lower you go with your TR, the lower you have to go with your flip angle to get full longitudinal recovery. There it is. What do we got? Any questions? It's all 100% clear? You'll have to answer some like this. There'll probably be just like 4 or 5 of these questions, maybe less, probably at least 4 probably. But you have to know spin echo pulse sequences. What are we doing there? What's that 180 degree doing? When is it transmitted? What do the TR and TE do for us? What tissues are bright and dark in T1 and T2 weighted images and why? Right? What is intrinsic contrast? What's extrinsic contrast? What happens to my time between 90 degree and my 180 if I increase my TE? Right? What's the difference between gradient echo and spin echo? What are the benefits of running one versus the other? What are the disadvantages of gradient echo? What are the advantages of gradient echo? And how do I achieve all of the different contrasts in gradient echo and in spin echo? Make sure you answer your forum post. Make sure you spent 2 hours total in the Imaging U. And then you know where to find me if you have any questions. Good? All right.